Akshaya, is the voice and the video clear? Okay. If you have doubts, you can ask me, Akshaya. See, if your mic is not working, you can type. I can read your doubt and I'll try to clarify it. Page number 95. Okay. So, what's your doubt in that? Sumit Paul, what is your doubt?
Hello, sir.
Yes, yes, I can hear you. What is your doubt?
Yes, sir. My doubt is in the length of the vector, sir. Exactly what significance does length of the vector means? The length of the column.
See, length of the column. Suppose you imagine that as a vector,
Yes.
then that indicates the distance from origin to that point
To
actually.
that
So
point. Okay. Okay.
yeah, so suppose if the vector is in the form of 1 1.
Okay. Okay. Okay.
So what I mean by 1 1, I'll just show you. Suppose you have a vector called v1, which is like this 1 1, right? So in the two-dimensional coordinate system,
That would be
the
the x and
point,
y coordinates of one
right?
and
So
one.
it's like 1 comma 1 here. So if you
Yes. Yes.
join
Yes.
this with the origin, you get a vector actually.
Mhm.
So it indicates the length of the vector. That means the distance from origin to this point.
Thank you, sir.
Damant,
Hello, sir.
yes, yes.
Sir, my doubt is regarding the number of orthogonal matrix we can form. Sorry, symmetric matrices we can form with that question, sir. Q elements 1, 2, 3, 2, Q
Yeah,
minus 1.
I'll open that question, okay? Yes. What is your doubt in this question?
Sir, I understood this, but my doubt is if we take second order,
Hmm.
then we will get some number of matrices.
Hmm.
If we take third order, we will get some more number of symmetric
Hmm.
matrices.
Hmm.
Are we adding all those number of matrices of all order up to Q
No, no,
n?
we are not adding. We are just looking at, suppose if it is n cross n, how many are possible? That's it.
Okay, but he mentioned total number of possible entries. Okay,
So
only for
he
n cross.
clearly said n cross n he specified.
Oh, sorry, sir. I thought that every possible matrix of order.
No, no, not like that.
Okay, that's it, sir.
Okay.
Thank you,
Lakshmi
sir.
Karun, yeah, welcome. Lakshmi Karunya,
Yes, sir.
yes. What is your doubt?
Yesterday you said about the rank of the matrix, sir. Can I
Yes.
say the rank of the matrix of any order can be minimum one, sir?
See, can you repeat your question once again?
The rank of any order matrix
Hmm.
can be once a minimum value of the rank.
See, you should say it in a proper way. You mean to say, suppose you take a non-zero matrix, any non-zero matrix, the rank of that is greater than or equal to 1. It can be greater than or equal to 1.
Okay.
This is what you mean to say,
Yes, sir.
right? So you take any non-zero matrix, because if you take a zero matrix, the rank is 0, na?
It's called the rank zero. Oh,
So
okay, sir.
in the beginning only I'm saying take a non-zero matrix, rank of such matrix would be greater than or equal to 1. Is that okay?
Yes, sir.
Okay. Devadish, what is your doubt?
Yes, sir.
What is your doubt?
Yes, sir. Sir, in the definition of minor, we can see that to get the minor of a particular element of a matrix, we need to delete the ith row and jth column. Then
See
we
here,
get the yes.
it need not be. See, what you
Okay.
delete any column or any row, it doesn't matter. What you do is delete few things and try to get a square matrix.
Square matrix, no, sir. Okay.
Every
Okay.
time you need not delete one column and one row. It's not like that.
Yes, yes.
Right?
For a non-square
Sometimes,
matrix, yes, yes, sir.
yeah, sometimes what happens is just by deleting a column, you get a square matrix. In some
Yes,
situations,
sir.
you're supposed to delete a column and a row.
Oh, yes, yes, yes. Okay, okay. Sir. Thank you.
Sindham,
Yes, sir.
your doubt?
So can you please explain problem 291?
Problem 291. What is that
Yes, sir.
about? Page number?
Page number I don't remember. It's about column
It's
vectors
about,
and row vector M and M inverse.
Okay, I got that problem. Mhm.
Okay, sir.
This one?
Yes, sir.
Okay. So what is your doubt in this?
So U1 transpose into V1 equal to 1, right?
Mm-hmm.
But why, sir?
Okay. Can you tell me how does U1 transpose look like?
U1 transpose looks like column vector.
How do you know that it's a column vector? Look at this definition of the problem. What is U1 transpose?
Row vector.
Then it's a row
U2
vector, correct?
Yes.
U1 transpose and U2 transpose both are row vectors. So
Yes, sir.
how does U1 transpose look like? See here, this looks like a row.
Okay.
Also a row. Okay, first row, second row. First row into the first column will give you this element.
First row into first column. Okay, sir.
That's how we do matrix multiplication.
Yes, sir, I know it. But why is it 1?
Because M inverse into M will always give you identity matrix.
Okay, identity matrix. Okay, sir, I got it.
Yeah.
Sir, but why we took M inverse into M? Why not M into M inverse?
See, yesterday also I explained why I have taken M inverse into M. The reason is, if I take M inverse, readily a row is available for me. Correct?
Okay.
If I take M into M inverse, how does M look like? V1,
V1,
V2,
V2,
and M inverse is like U1 transpose,
U1 transpose,
U2
U2
transpose.
transpose.
Now here I need a row and here I need a column. So it becomes difficult for me.
Okay.
V1, V2 are columns, but I need row, and the other matrix I need a column.
Okay, sir.
So I'm not
So
going for...
M inverse M would be easy for us.
Yes, yes.
Okay, sir. Thank you, sir.
Okay. So one more last. Don't worry if I'm not able to take your doubt. At the end also, like, so from 4 to 6, I'll take a class. I'll give a break. In that break also, you can ask me. Kiran Kumar.
Hello.
Yes.
Hi, sir. My question is, if I take a 4x4 matrix and if the minors, like by deleting a row, we can get 3 minus, and by deleting a column also, we can get 3 minus. So the total minus would be 6 or 3. Like 3 is enough to check the rank. Like if we want to check the, like let's say determinant of 4x4 matrix.
You are talking
is 0.
about a 4x4 matrix?
Yes, sir. 4x4.
Okay. You want to find rank?
No, I am concerned about the minor definition. Like if I want to check.
No. See here, first of all, if you want to find the rank, there is one alternate way. Okay.
Yeah, okay.
If you want to check the minor, suppose you want to check 3x3 minor.
Yes, sir.
You just remove one column every time.
Yes, sir.
Okay.
But
so
by removing column, we can get three matrices, 3 by 3.
Yes, yes.
By removing row also, we can get 3.
Okay. You want to remove a row? See here, for 4x4 matrix, if you want to get a 3x3 minor, you have to remove both row and column actually, not just one column. That is not possible.
Okay. Okay.
Is that clear? You are saying like 4x4, you want to remove one column, but that is not possible. One row, one column you have to remove.
Okay.
Yesterday example was about a 3x4 matrix.
3x4 matrix.
That is different problem.
Okay.
Yeah.
Okay. That is the question.
Yash, what is your doubt?
Sir, I had a question. Sir, the question.
Wait a minute. Yesterday, not only yesterday, day before yesterday also, there was one doubt that you people have asked. Who is that? Yes, you are the one or someone else?
Sir, no, I didn't ask. Sir, but I remember that doubt was regarding, I think, basic columns of A.
Yes.
Yeah, linear dependency.
Once you complete your doubt, I'll go with that explanation also. Okay. Yeah, you can continue with your doubt.
Sir, A is a matrix given. It is a 2 cross 2 matrix, 6, 7, 2, 2.
Okay.
Sir, we have to find the determinant of A raised to the power 2004 minus 2A raised to the power 2003.
Yeah, we
Sir,
will discuss this. Don't worry.
Okay, sir. And
You
sir,
wait a minute. A raised to power 2000?
2004
Hmm.
minus 2A raised to the power 2003.
So what you can do is in the first step, you can take A raised to 2003 common. What is left is A minus 2I.
Yes, sir.
Now you can take determinant on both sides. So this is determinant of A, I mean not both sides, I'm just saying take determinant. So this is determinant of A power 2003 into determinant of A minus 2I. You can find determinant of A minus 2I. Det A also you can find.
Yes, sir.
So that's how you need to solve.
So there's one more question. So let A be a 2 cross 2 matrix with non-zero entries and A square equals to I. And there are two statements. Trace of A is 0 and determinant of A is 1. So
he says A is a non-zero matrix.
Yes, a 2 cross 2 matrix with non-zero entries and A square equals to I. Yeah.
So what is he asking? Is he asking trace of A?
Is 0. So first statement is trace of A is 0. And the second statement is determinant of A is 1.
Okay, we are yet to discuss this. Once we complete eigenvalues and eigenvectors, you can try it. I'm not saying that you will surely get the answer, but you will get some better ideas to tackle this problem.
Yes, for sure, sir.
There are some properties that relate trace and determinant of a matrix with eigenvalues. Okay, so if you can wait, I'll explain that.
So just one more doubt.
See, I'm saying that we will be talking about eigenvalues and eigenvectors. Once we complete, go through that.
Okay.
Try to do on your own. If you don't get, you try to mail me or post it in the Telegram channel. We'll help you.
Definitely, sir. So the next is regarding rank. The rank of a M cross N matrix where M is less than N cannot be more than. The option is M, N, Mn and none.
A is a M cross N matrix where M is greater than
less than N.
So what we understood yesterday is rank of A is always less than or equal to
minimum of M comma N.
So clearly min of M comma N is M.
Yes, sir.
So the rank of A is less than or equal to M now. So it is definitely less than or equal to M. It cannot be N.
Sir, but when M is less than N, then definitely it will not be greater than N also.
That's what. Accordingly, you have to choose the options now.
Sir, according to me, M and N both should be the answers, and even Mn also. Because
no. What are the options?
Sir, M, N, Mn and none.
Can you read the complete question? A is some M cross N matrix where M is less than N.
The rank of this matrix cannot be more than. The A option is M, the B option is N, and C
you are right. You are right.
Yes, sir. But the answer is given as M only, I think.
Cannot be more than.
The answer is M, sir.
See, the question, the person who has prepared should have done it in a proper way. So there should not be any option called N actually. So technically speaking, the rank will always be less than or equal to M. Okay?
Yes, sir.
So it can't exceed M first of all. So you should have created option this way.
And sir, when it cannot exceed M, then it cannot exceed N also, I suppose.
Yeah, that's what. Yeah. So your argument is right.
Okay. Thank you, sir.
Okay. So what I'll do is I'll continue with this discussion. Okay. Akshaya Vanam, I'll come back to you, yaar. Akshaya Vanam, I'll come back in the break time. I'll discuss your doubt. So let's go ahead. And who was that? I'll lower the hands, all the hands. Yesterday, someone was pointing out. There was a girl actually who was talking about some homogeneous system. So can She raised the hand once. Yesterday, one of the student gave some homogeneous equations. So if she's there, she has to provide me that question now so that I can solve it. Okay, so let's continue the discussion. Let me start this discussion with some homework problems. Vaishnavi,
Yes, sir.
you were giving some homogeneous equations yesterday?
Yes, sir. That
Yeah.
if the numbers are in HP or that.
No, not like that. Some x plus
Yes, sir.
3a,
Yes, sir.
something like that.
Yes, sir.
So I'll ask you that question. Whenever I ask you, try to provide me. Okay, make sure you
Okay,
have
sir.
that question with you.
Yes, sir.
Okay. Now let's do this homework and then continue the discussion. What is he asking? He's asking you to find what could be the expression for adjoint of adjoint A. So let's see how do we handle this. First, let me write that A inverse is adjoint A by det A. From this, if I do the rearrangement, I get adjoint A equals det A into A inverse. Now, the discussion is about adjoint of adjoint A. For a moment, what I'll do is I'll just assume that let adjoint A be B. Okay, so let's say let adjoint A be B. So then what happens is your problem reduces to adjoint B because in the place of this you have substituted B now. So now we know that adjoint B is simply det B into B inverse. So how did I get this? See here, I've used this point. Adjoint B is det B into B inverse. Now I would like to substitute what is B. B would be adjoint A det and then B inverse, that is adjoint A whole inverse. Let's see what is det of adjoint A. Yesterday also in the class, we have gone through this. Det of adjoint A is det A power n minus 1. And adjoint A whole inverse is something like det A into A inverse whole inverse. Upon simplification, you get det A power n minus 1 into det A power minus 1 into A inverse whole inverse. So let's see what could be the final step here. So I can club this and this. This is now det A power n minus 2 and this is A. So what is the expression for adjoint of adjoint A? The expression is det A power n minus 2 into A. We are now supposed to look at the determinant of that quantity. So how do we find the determinant of that quantity? So what are you supposed to investigate? We are supposed to investigate what is adjoint of adjoint A determinant. Just now we understood that this particular adjoint of adjoint A is det A power n minus 2 into A. I would like to remind that the determinant of C alpha is alpha power n into the det of C. In the same way, this could be det A power n minus 2 whole power n into the det of A. So here the alpha, this is like alpha, okay? So what do we get is, we get det A power n into n minus 2 into det A power 1. You can club all this, right? That this is det A power n square minus 2n plus 1, which is nothing but det A power n minus 1 whole square. So these are the two problems that I gave as homework. So let me fill this here. This is det A power n minus 1 whole square. I hope you people would have also tried this. Okay, so let me go ahead with the discussion. Like I said, while solving system of homogeneous equations, we have used only the row echelon form approach. We haven't used determinant concept. Okay, I would like to invite a student and ask few questions. Okay, Vaishnavi, are you there?
Yes, sir.
Vaishnavi, can you tell me what is rank of non-singular matrix?
Hello, sir.
Yeah, what is rank of a non-singular matrix?
Uh,
Non-singular means determinant
Det
not equal
is not
to
equal to
0.
0.
So what could be the rank of such matrix?
It can be its order, sir.
It is not, it can be.
It
The
is its
rank
order.
is, it is its order, correct?
Yes, sir.
Suppose, and let me ask you another question. Suppose
Yes.
if you have a singular matrix, what would be the rank?
It is less than its order, sir.
Very good. It's less than its order. Now, I just want to tell all the people that suppose if I say the rank is less than its order, rank is less than its order, then can I say that the determinant of that matrix will go to 0? I'm saying rank is less
Yes.
than its order. So I can say that the determinant will definitely go to what?
0.
0. Okay, nice. So let me read this problem and I want suggestions from you people. It says, consider a matrix called A. Consider a matrix called A and a vector X. The number of distinct real values of K for which the equation Ax equal to 0 has infinitely many solutions. He clearly says he wants what? Infinitely many solutions. When do you get infinitely many solutions? Any answer from you, Vaishnavi?
Yes, sir. When rank of AB is not equal to.
There is no B here because it's a homogeneous
Okay.
system. We just need
When,
A only.
yes, sir. Yes, sir.
I'll help you.
Yes, sir.
When rank of A is less than number
Rank.
of unknowns.
Yes, sir.
Correct?
Yes, sir.
In that situation, you get infinitely many solutions. Correct? Here,
Yes, sir.
by looking at this vector X, by looking at this matrix A, I see that the number of variables involved is 2. How do I know that number of variables involved are 2? Because x1 is given, x2 is given. So the number of variables involved are 2. So to have infinitely many solutions, the rank of A must be less than 2. Correct?
Yes, sir.
When rank is less than 2 and A is of the order 2 cross 2, definitely A should be what? Singular.
Yes, sir.
That means the determinant of A should go to what? 0. So by equating the determinant to 0, you get some condition. You just solve that and get the values for K. So for example, what would be the determinant here? The determinant would be K cube minus 2K into K square minus K equal to 0. So this is like K cube minus 2K cube plus 2K square equal to 0. So this is like minus K cube plus 2K square equal to 0. Let me solve for K. I can take minus K square out. So what is left is K minus 2 equal to 0. The values of K are 0, 0 and 2. Now tell me, Vaishnavi, how many values of K you have got?
2, sir.
We got 3 values for K, but in the question, they're asking clearly about the distinct real values of K, correct?
Yes.
So what could be the number of distinct real values of K? It would be 2.
2.
Because 0, 0, 2 means the distinct values are 0, 2. Therefore, the final answer for this question is 2. Right?
Yes.
I would like to again and again tell you that, see, to have infinitely many solutions, we need rank of A to be less than the number of variables. The number of variables in this question are 2. So the rank must be less than 2. the order of A is 2 cross 2. When you say rank is less than its order, then that matrix determinant must go to 0. So based on that, we got values for K. We don't see, he clearly in the question wants distinct values. So because of that, I say that 0 and 2 are the two distinct values. So the answer is 2 here. Now, I'll go to the next problem. I would like to ask now the student to just read out the question that she was asking yesterday. What was that question?
Yes, sir. If the system of equations x plus 4ay plus az equals to 0,
Okay.
x plus 3by,
Hmm.
3by, sir, plus bz equals to 0, and x plus 2cy plus cz equals to 0
Yes.
has non-trivial solutions, then A, B, C are in
As non-trivial
solutions.
solution.
Then,
Now, can I say non-trivial solution means infinitely many solutions, na?
yes, sir.
Okay. So now what I can do is we need infinitely many solutions. So for that, let's create a matrix A. Matrix A would be like 1, 4A, A, 1, 3B, B, 1, 2C, C. Now for non-trivial solution, what we want is we want rank of
Rank of
A
A.
to be less than 3 actually.
Yes.
When you say that A is a 3 cross 3 matrix, A is a 3 cross 3 matrix and its rank is less than 3, that means its determinant should go to 0, na?
Yes, sir.
Its determinant should go to what? 0.
0.
So the det of A is 0. Equating the determinant to A to 0, you get a condition in ABC. You get a condition in ABC, am I right?
Yes, sir.
Based on that, you decide the relation between ABC,
Okay, sir.
right? So the remaining work, I'll just give as homework. Then I'll just write the question has non-trivial solution, then the relation between A and B. Okay, so equate this, you
Yes,
get
sir.
some condition in A and B. So based on that, you have to answer the homework problem.
Yes,
Right?
sir.
Again and again, I'm saying that it's a homogeneous system and you want a non-trivial solution. What you can do is you can simply equate the determinant of A to 0. That's the logic here. I hope this is clear.
Yes, sir.
Now, I'm going to talk about the most important concept, that is linearly independent and dependent vectors. In the first class also, in every class, I have been talking about linearly independent vectors. While talking about the rank, also we had this discussion. So I would like to tell you like what does this mean. Okay, so for that, let me invite few students ask their opinions. Okay, let's invite Devadish. Randomly I'm inviting. Okay, randomly I'm inviting Devadish.
Yes, sir.
Are you ready to answer my question?
Yes, sir.
Devadish, look at V1, read V1.
So V1 equal to 1, 0.
Read V2.
V2 equal to 2 zeros.
Do you see any relationship between V1 and V2?
Yes, sir. I can say that V2 equal to 2 times of V1. Yes.
2 times V1.
V1.
Now, I just want to say that V2 is expressed in terms of V1. Am I right?
Yes, sir. Yes.
That too, I have used a linear relationship.
Yes, sir.
So because of this, we say that V1 and V2 are linearly dependent. Linearly dependent because you are able to express V2 in terms of V1. Is that okay?
Yes.
Now see the alternate way, my dear students. Look at the alternate way. You said V2 is 2V1, na? Can I write
Yes.
this as 2V1 minus V2 giving me a zero vector?
Yes, sir. We can write.
Just I rearranged it, right?
Yes, sir.
This looks like something like alpha 1 V1 plus alpha 2 V2 giving you a zero vector. Am I right?
Exactly, sir. Yes.
When you say alpha 1 V1 plus alpha 2 V2, are you taking the linear combination of these vectors?
Yes, sir.
Right? Can you also provide me what was alpha 1?
Yes, sir. In here, alpha 1 equal to 2. Yes, sir. Minus 1, alpha 2.
Very good. Not only this, see here, alpha 1, if I put 4, alpha 2 can be minus 2, you know.
Minus 2, yes. Just.
Am I able to generate many solutions for alphas?
Yes, sir. We can generate.
Suppose 6 here, alpha 2 is minus 3. Will that be okay?
Yes, sir. We are
Right.
3 times. Sir. Yes.
How many solutions you are able to generate?
Infinite solutions we can generate in this step. Yes.
Infinitely many solutions. Okay.
Yes.
Okay, nice. This is one more observation. See, finally, what's the comment? Is V1 and V2 linearly dependent or not?
Yes, sir. V1 and
What's
V2
the
are
question? What's the question? Read this.
Are the vectors linearly independent? No. These are
No, they
linearly
are linearly dependent.
dependent.
In the exam, the easiest way is form a matrix using V1 and V2. Form a matrix. How does that look? 1, 0,
Yes.
2, 0. The determinant of this is how much?
0.
0. Whenever the determinant goes to 0, you can call those vectors to be linearly dependent.
Dependent.
This is alternate way. Alternate way. So conclusion is V1 and V2 are linearly dependent. Okay, linearly dependent. Let me ask another student. Yeah. Damant, are you there?
Hello?
Yes, Damant, are you there?
Yes, sir, I'm there.
Okay, Damant, read this example too.
Consider the vectors. V1 is a column vector of 1, 0, 0. V2 is 0, 1, 0. V3 is 1, 1, 0. Are the vectors linearly independent?
I'm trying to explain you people about linearly independent and dependent vectors through some examples. Okay. My question is, Damant, observe V1, V2, V3. Do you see any relation between them?
Relation. I don't see any relation, sir. Maybe I'm not able to observe actually, but the debt is becoming 0, sir.
The debt is becoming 0. Okay, nice. Come on. Once again, I'll give you 10 seconds.
Okay, sir, I will try.
Other students, you also be ready. Okay.
Sorry, sir, I was not able to find any relation between.
It's okay. It's okay. See here. Look at V3. V3 is V1 plus V2. Do you agree to me or disagree?
I agree, sir.
That's what I asked. Like, can you see any relationship between V1, V2, V3?
Okay, I'm checking for just multiples. I mean, multiplying 2 times or 3 times like that.
That's also fine. Fine. So, can I say that I have linearly related V1, V2, and V3?
Yes, sir.
Or simply using V1, V2, I have expressed, or using V1, V2, I got V3?
Yes, sir. One dependency.
Yes. So what I can say is I can rewrite this as V1 plus V2 minus
V3 equals to 0.
A zero vector. Correct?
Yes, sir.
Therefore, the conclusion is V1, V2, and V3 are what?
linearly dependent vectors.
Yes. Now let's look at something like this. Alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 should give me a zero vector. Can you provide me some alphas? One
Yes,
choice is already on the screen. Alpha 1 is 1.
1 and -1 alpha 3.
Can you provide me another choice?
3, alpha 1 is 3, alpha 2 is also 3, alpha 3 is -3.
Can you give me many other choices?
Yes, sir. Oh, if first two are k and k, the third one becomes
Ah,
-k. We can choose any
very good.
values.
Very good, good. Nice approach. Finally, for a equation like this, how many solutions you have?
Infinitely many solutions.
Infinitely many solutions. Nice, very good. Are they linearly dependent?
Yes, sir.
Okay, what could be the alternate approach?
Finding the determinant of these 3 column vectors.
Okay, so let's do that. V1, V2, V3, 1, 0,
1
0.
0 0 1 0 1 0 1 1 0
What is the last row?
0 0 0.
When a row or a column is entirely 0, what could be the determinant of that?
0, sir.
So the determinant here is 0. Whenever you take those vectors, form a determinant, and that determinant goes to 0, what's the conclusion? V1, V2, and
V2
V3 are.
are linearly dependent.
Now, if the determinant is non-zero, in such case, they are linearly independent. Okay.
Yes, sir.
See here, I would also like to say that you said infinitely many solutions. Now, one more choice is also there. Alpha 1 equal to alpha 2 equal to alpha 3 equal to 0. Can this also be a solution? Yes.
Yes,
but
sir.
we are actually looking for those alphas. We are looking at those alphas where at least one alpha is non-zero.
Okay.
Right. So don't tell me every time alpha 1, alpha 2, alpha 3 equal to 0. Try to give me a set where at least one of them is non-zero.
Okay.
Okay.
Yes.
Yeah. Let me
So
go to the.
is this related to some nullity of the matrix?
Yes, it's
Homogeneous.
also related to nullity.
Okay.
Just wait till the entire course gets over. Okay.
Sorry. I mean, mentioning it as 0, I thought it is a concept of nullity.
Yes, yes, it's related to nullity also.
Okay, sir.
Lakshmi Karunya, are you there?
Yes, sir. Yes.
Yeah, can you read this?
Consider the vectors v1 1 0, v2 0 1 are the vectors linearly independent.
So we will go by the easiest approach. What is the easiest approach?
Finding det one.
Yeah, alternate approach is through the determinant. So let's construct a matrix called V1, V2 like this. 1 0 0 1. What is determinant of this?
1, sir.
That means what? It's not equal to 0.
0.
Therefore, V1 and V2 are
Linearly independent.
linearly independent. Is that okay?
Yes, sir.
Now, when the vectors are linearly independent, you know what does it mean? It means that those vectors, that means using V1, you cannot express V2 in a linear way. Right? For example,
Yes, sir.
look at this. Alpha 1 V1 plus alpha 2 V2 equal to a zero vector. Can you provide me alpha 1 and alpha 2 values?
Sure.
My dear students, can you people provide me the values of alpha 1 and alpha 2 such that alpha 1
0,
V1?
sir.
Okay, I'll come back to you. Can you people provide me alpha 1, alpha 2 such that alpha 1 V1 plus alpha 2 V2 is giving me a zero vector? One of the students says alpha 1, alpha 2, both of them equal to 0. My dear student, do you have any other alphas apart from that? Do you have any other alphas apart from that? The answer is no. There is only one solution, that is alpha 1 and alpha 2, both of them equal to 0, correct? Okay. So my dear students, I want to say that there is only one solution which satisfies the above equation, that is alpha 1 equal to alpha 2 equal to 0. But I'm not looking at this solution. I want a solution such that alpha 1 v1 plus alpha 2 v2 will give me a 0 vector. At the same time, one of the alpha i's must be non-zero. So the only solution possible, so I'll just name it as 1. The only solution possible is the trivial solution. The only solution possible is the trivial solution. Therefore, v1 and v2 are linearly independent. In the exam, you don't need to look at the solutions. In the exam, what you people have to do is go through the determinant approach. That would be the easiest approach. Go through the determinant approach. That is the easiest approach. Let me put some more examples in front of you. Let's say consider the vectors v1, v2, v3. Are the vectors linearly independent? So what I would like to do is I would like to go by the easiest approach. v1, v2, v3. I would look at the determinant of this 1, 0, 0, 0, 1, 0, 0, 0, 1. Clearly, this looks like a identity matrix whose determinant is 1, which is not equal to 0. Therefore, v1, v2, and v3 are linearly independent. So what does this mean? You cannot have a linear relationship between v1, v2, v3. So using v1, v2, you cannot express v3. Using v1, v2, I cannot generate v3. That's what it means. So again, we will write something like this. Alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. Suppose if this is equation 1, then the only solution possible is alpha 1 equal to alpha 2 equal to alpha 3 equal to 0. There is no other solution possible. Suppose if there is a non-trivial solution, that means you are able to generate some alphas which are non-zero. In such case, the given vectors would be linearly dependent, but that is not the case here. Therefore, the given vectors are linearly independent. So this is example 4. Let me put some more examples in front of you. Example 5. In example 5, he has given us four vectors, and they're asking whether they are linearly independent or not. Let me examine those four vectors clearly. So you people, what you will do is, first you will put the heading called the easiest approach. That is, you will look at v1, v2, v3, v4. You would like to find the determinant, right? So let's generate that matrix v1, v2, v3, v4. The determinant approach will fail here. The determinant approach fails here because it's a 3x4 matrix, right? You can't find the determinant. When you are unable to find the determinant, what you will do is you will find the rank actually. See here, earlier cases, what I've done is I've said find the determinant. In the exam also, there were a few times where the question appeared from this topic. Those questions were like easily solved using the determinants. But suppose if he gives a vectors like this v1, v2, v3, v4, whether they are linearly dependent or not, how do you decide this? You need to find rank. So what is rank of this matrix? clearly this is already in row echelon form. Already in which form? A row echelon form. If it's already in row echelon form, what could be the rank? It is simply the number of non-zero rows. So the non-zero rows are 3. There are 4 vectors, but the rank is 3. There are 4 vectors, but the rank is 3. There are 4 vectors, but the rank is 3. Okay, now what the conclusion is? V1, V2, V3, and V4 are linearly dependent. Okay, V1, V2, V3, and V4 are linearly dependent. Suppose the rank was 4 and 4 vectors were given, then you could have said that the given vectors are linearly independent. Okay, I would clearly mention that point. I need some space, so I'll just copy this. Here, rank equal to 3 indicates that there are 3 linearly independent vectors among the 4. Among the 4 vectors. Okay. See here, rank will always indicate the linearly independent columns or whatever it is. Okay, it indicates linearly independent columns or rows. Here I'm talking about vectors. Okay, so I'll again and again I'll tell you how do you handle when the determinant is not possible. First, form a matrix, find the rank. What's the rank here? It's 3. How many vectors were given? 4 were given. How many vectors were given? 4 were given. What was the rank? It was 3. So what is this telling us? Among the 4, there are only 3 linearly independent. That means the leftover one can be expressed as linear combination of 3 vectors. That's how you need to understand this problem. Okay, so v1, v2, v3, and v4 are linearly dependent. Here rank equal to 3 indicates that there are 3 linearly independent vectors among the 4. So finally, are the vectors linearly independent? The answer is no, they are not linearly independent. Not only through this rank approach, you just observe this. You can write v4 as v1 plus v2 plus v3, right? So you can easily understand that if you add v1, v2, v3, you get v4. Indirectly, this is something like v1 plus v2 plus v3 minus v4, giving you what? 0 vector. Here alpha 1 equal to 1. So we have something like alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 equal to what? A 0 vector. One choice of alpha is like this: 1, alpha 2 also 1, alpha 3 is 1, alpha 4 is minus 1. I can give you another choice. Alpha 1 is 2, alpha 2 is also 2, alpha 3 is also 2, alpha 4 as minus 2. Like that you can generate many solutions. So what are these? These are all non-trivial solutions. So whenever you have non-trivial solutions for that alpha, v1, v2, v3, and v4 are linearly dependent. Okay. Yeah, so I see many students having doubt here. Okay, I'll take those doubts. Don't worry. See here, before I take all those doubts, I'll explain you once again. See here, 4 vectors were given to you. 4 vectors are given to you. So I'll explain you this again. I'll write it in detail. V1, V2, V3, and V4 form linearly dependent set. Linearly dependent set. Now, in that linearly dependent set, we have three linearly independent vectors. In that linearly dependent set, we have three linearly independent vectors. How do I know that? Because rank of v1, v2, v3, v4 gave me 3, right? So this is one such example. Let me create another example. Yeah, let me create another example. Let me go to the next page. Let's say example 6. V1 is something like this. V2 is like this. V3 is like this. V4 is like this. I clearly see that V2 is simply 2V1. V3 is 3V1. V4 is 4V1. Okay. Now, clearly there is a linear relationship. Clearly there is a linear relationship between the vectors. So there is no doubt. I'll say the given vectors form a linearly dependent set. Now, in that linearly dependent set, I want to know how many are linearly independent. In that linearly dependent set, I want to know how many are linearly independent. So how do I find that? For that, what I'll do is I'll write all the vectors together. How does that look? It looks like this. It looks like this. Clearly, the rank here is 1. That means the given set is linearly dependent and there is only one independent vector. Okay, so I'll write that conclusion. In the given linearly dependent set, we have one linearly independent vector. That means the remaining 3 vectors have been generated using only this vector itself. That's what is the meaning. I hope I would have cleared your doubts. First of all, I'm looking at a linearly dependent set. In that linearly dependent set, how many are linearly independent? How do you decide that? Take all those vectors, form a matrix, find the rank of that. That rank will tell how many are linearly independent in that linearly dependent set. Here, I would like to also highlight this point. Look at this. This is an example where V1, V2, V3 form a linearly independent vector set. In that linearly independent vectors, you take any 2 vectors, right? Suppose there are n linearly independent vectors, you take any or some of those vectors, those sum of the vectors, that is, suppose there are n linearly independent, let's say you take r of them, those r are also linearly independent. Okay, I hope this discussion is very clear. If you take a linearly independent set, let's say there are n vectors in that, from those n, let's say if you pick r, those r are also linearly independent. That's the conclusion. Now the same thing, if you take a linearly dependent set, right? So you cannot apply the same logic to linearly dependent set. So that's about linearly independent and dependent vectors. I took some examples to help you or to make you understand linearly independent and dependent vectors. Let me give you the definition of linearly dependent and independent vectors now. Okay, so let me go through that definition once. So he says, so the topic now is about linear independence. For that, we need to take set of vectors. What does S represent? S represent set of vectors. How many vectors are there in S? There are n vectors. A set of vectors is said to be linearly independent set whenever the only solution for the scalars, that is, whenever the only solution for the scalars in the homogeneous equation. What is a homogeneous equation? This is the homogeneous equation. Why this is called homogeneous equation? Because on the right hand side you see a zero vector. This is referred as homogeneous equation because on the right side you see zero, right? When the only solution possible is the trivial solution, in such case the given vectors are said to be linearly independent. Suppose non-trivial solution exists. Suppose non-trivial solution exists. In such case, the given vectors are said to be linearly dependent set. That is given the next point. So let me read the second point. Whenever there is a non-trivial solution for the alpha, whenever there is a non-trivial solution for the alpha, the set S is said to be linearly dependent set. Okay, so it's very simple. Let's summarize the thing. So how do you summarize? So I would like to summarize it in the following way. Alpha 1 V1 plus alpha 2 V2 plus so on plus alpha n Vn. This is the homogeneous equation. Now for this homogeneous equation, if you have only the trivial solution, if trivial solution is only possible, then such set is called linearly independent set. Suppose if you say a non-trivial solution exists, suppose you say non-trivial solution exists, then it is called linearly dependent set, right? Don't think too much about this. In the exam, what he will ask is, he will give you some set of vectors. He'll ask you whether they are linearly independent or not. Most of the time, just by the determinants you can tell. Just by looking at the determinants you can answer, right? So don't get confused. Just by determinants concept you can answer the questions. So this is about linearly independent and dependent vectors. I would like to put some problems in front of you now. This particular problem was asked in GATE 2021. What was that problem? My dear students, let me first complete the concept, only then I'll take your doubts. Okay, please excuse me for that. Around 7 o'clock, right? Around 7 o'clock, I'll be taking up your doubts. Not 7, I guess, 6 o'clock. 6 o'clock. If the vectors, okay, he gave 3 vectors are linearly dependent, then what's the value of x? See here, whenever he gives you a question like this, now you get a doubt. Should I take this as a row vector or a column vector? Anything is also, I mean, you can take it in the form of column, you can take it in the form of row, it doesn't matter, right? I usually take it in terms of column. If you want, you can take it in terms of row, it doesn't matter. Okay, so what I'll do is I'll take them in terms of row, it doesn't matter. Okay, 1 minus 1 2 7 3 x 2 3 1, I'll equate the determinant to 0 and then get the value of x. Okay, so let me expand the determinant using the first row. Equate this to 0. So this is 3 minus 3x, 7 minus 2x, 15, so this is 30 equal to 0. 40 equal to 5x, I guess. So the value of x is 8. So if at all they ask the questions this way. The value of x is 8. What is the logic that we have used? He gave that the vectors are linearly dependent. Now some of the students might be saying, sir, you have taken in terms of row, I'll do in terms of column. If you do in terms of column also, it would be same. Yeah, don't worry. If you want, you can check it. So that's the answer for this question. Let me put one interesting problem in front of you. What he says. He says, consider the following statements. If x1, x2, x3, x4 is linearly independent set, then the set x1, x2, x3 is linearly independent. That is statement 1. Statement 2. If x1, x2, x3, x4 is linearly dependent, then the set x1, x2, x3 is linearly dependent. We need to tell which is true, which is false. If you have followed those examples clearly, you would easily understand this. I would like to first take 4 vectors like this. Always keep in mind the best choice would be the columns of the identity matrix. Clearly, V1, V2, V3 and V4 are linearly independent vectors, right? So what is this? This is the analysis related to S1. This is the analysis related to S1. So now to understand whether S1 is true or not, I have taken 4 vectors which are linearly independent. Now after that, what I should do? I should look at any 3 of those vectors like x1, x2, x3 or v1, v2, v3. So let me take v1, v2, v3. The determinant logic will not work because they won't form a square matrix. So what you get is this. This is not a square matrix. So what you can do is you can find the rank. The rank here is 3. Clearly, the vectors that you have taken v1, v2, v3 are also linearly independent. My dear students, remember, if you have n vectors which are linearly independent, and if you take any r of them, for sure those r are also linearly independent. Okay, so I'm going to write that here. V1, V2 and V3 are linearly independent. So what is that point we are going to highlight? Look at this point. If V1, V2, so on, Vn if v1, v2, so on, Vn are linearly independent vectors, then if we take any r of the above vectors they are also linearly independent. Okay, so that's the answer for this. So what I can say is S1 is true actually. Suppose if V1, V2, so on, Vn are linearly dependent vectors, and if we pick any R of them, so here clearly R is less than n, na? So here also R is less than n. If V1, V2, so on, Vn are linearly independent vectors, and if we pick any R of them, then those R vectors may or may not be linearly dependent. Maybe I should have written like this: may or may not be linearly independent. Okay, so this is about the S2 statement. S2 statement. He gives you 4 vectors. He's asking, he has taken 3 vectors. Will that 3 vectors be linearly dependent? The answer is they may or may not be linearly dependent. You can also write they may or may not be linearly dependent as well. Okay, so sometimes it may be linearly independent, sometimes it may be linearly dependent. I hope this is clear, right? The same statement you can write, you take this, you take this, you take this, and at the end you put linearly dependent. Even that is also true. Even that is also true. So here also R is less than n. So now what's the conclusion about the second statement? So I'll just put it for you because some students may get confused here. Let's copy this. Here, if you put D, even that is also fine. This is also true. Then those R may or may not be linearly dependent. This is also true. So I can say that S2 is false. S2 is false. Now, if you ask me example, already examples I have written. Check it. Look at this. This set in the example 5, the given vectors are linearly dependent. Now, if you pick the first 3, this and this and this, they are actually linearly independent. Okay, so in this question it is working. The first 3 vectors are linearly independent. Go to the 6th example. Look at this. The set is linearly dependent. If you pick the first 3, they are not independent, they are actually dependent. That means what? If you have a linearly dependent set, if you pick some of the vectors, those vectors may or may not be linearly independent. Okay, so that's the answer here. So we are done with this problem as well. This completes the discussion about linearly independent and dependent vectors. What kind of questions you may get from this topic? What kind of questions you will get is, he will give you some vectors, like 3 vectors or 4 vectors. Most of the time, I have seen the questions. What they have done is, when you form a matrix, it would be a square matrix. Just by equating the determinant to 0, if the determinant goes to 0, then they are linearly dependent. If the determinant is not equal to 0, then they are linearly independent. Most of the questions can be solved with this logic itself. Okay, so that is about linearly independent and dependent vectors. I would like to take some doubts here because this is such an important topic. I would be very happy to take doubts. Vamsi Krishna, what is your doubt? The problem is, if I take the doubts, everyone will ask the same doubt. Okay, Vamsi Krishna, what is your doubt?
Hello.
Yes.
So in example 5,
Hmm.
example 5, can you open example?
Yes.
Here actually you did mistakes, sir. Like
Yeah, what is that mistake?
the linear alpha 1 v1 plus alpha 2 v2, the sum is not equals to 0 there, sir.
The sum is not equal to 0?
Yes. With the values of alpha you considered. Sir.
Okay, okay.
Actually, we need to consider alpha 4 as 0, I think.
No. I think there is some mistake in the way I created the vectors. So let me change this vectors. I understood this is actually correct. 1, 1, 1 is correct here. So this is something like 0, 0, 1 actually. Is that okay now?
Yes, sir, it's okay now. And here in the right side, you wrote about rank equals to 3, sir.
That is also I'm changing. That's 0, 0, 1.
No, can you brief about it again, sir? About the right hand
First of
side.
all,
topic.
let me tell the corrections to the entire class.
Okay.
The first thing is, I wrote something here and I was imagining something else. Okay, so I couldn't get that. First, let me change the vectors as I have changed v3 as 0, 0, 1. Okay, now everything will work actually. Everything, whatever I wrote, is going to work if v3 is this. Now, first thing that I want to check is whether they are linearly independent or not. So for that, is this relation true, Vamsi?
Yes, sir.
No, this is true. So clearly from this, they are actually linearly dependent. Okay.
Yes.
Further, what I would like to do is, suppose in the exam, what happens is, just by looking at the vectors, you will not be in a position to write equation like this.
Yes.
Because in the exam, he'll give you some random values. Random values he'll give, na? So you will not be in a position to directly write it. In such case, what you can do is you can find the rank here. Okay, what is order of this matrix?
3 by 4.
3 by 4. What is the rank that you have got?
3. Now,
3.
Yeah, 3.
How many vectors are given to you?
4 vectors.
But what was the rank that you have got?
3.
So what is this telling you is, the rank will tell you how many are linearly independent. How many are linearly independent? Only 3.
So whatever be the rank number indicates the linearly dependent vectors.
Yeah,
or
linearly independent vectors.
Yeah, linearly independent vectors. Okay.
Suppose if the rank was 4, let's say, if the rank was 4, let's say, then whatever vectors were given to you, they form a linearly independent set. But is the rank 4? No, it's 3, na?
3. Okay.
Yeah, thanks
So
for highlighting that. Yeah.
So again here, is there anything about this basic column and non-basic column comes into
not
point?
needed here. Not needed.
Okay. Thank
Rakshit, what is your doubt? Rakshit, what is your doubt?
Hello, am I audible?
What is your doubt? You're audible.
Yeah, sir, here in the same question, if instead of 4 column vectors, we are given 3 row vectors which form the same matrix. So what would be the answer for that?
Can you just give me those vectors? I'll write it. What you are saying?
Okay, 3 row vectors are given. V1.
Okay, 3
1
row
0
vectors
0 1.
like this. Okay, just a second. Are you giving me the entries of vectors or matrix?
Yes. The whole matrix V1, V2, V3.
Yeah. V1, V2, V3. Give me the entries.
1 0 0 1.
You mean me to write in the terms of columns or rows?
Rows.
1
1 0 0 1. Second row 0 1 0 1. 0 0 1 1.
But how many vectors are given here? 4 vectors are given, na?
3 vectors, 3 row vectors.
Okay, what you want to know?
I want to know, see the rank, the vectors given are 3 and the rank is also 3 for this matrix. So
Okay.
will it be a linearly independent set?
I mean, they'll clearly mention whether it's a row vector or a column. See, you said 3 row vectors are given, na?
Yes.
So you mean to say this vector,
Yes, correct.
this vector, and this vector. Firstly, they'll say that v1, v2, v3 belong to r power 4.
Okay.
Because look at this 1, 0, 0, 1 means there are 4 components here, na? So you are saying v1 is like a row vector.
Yes.
v2 is also a row vector. v3 is also a row vector. Okay, the rank here is 3. So if you treat them as row vectors, then they are actually linearly independent.
Okay.
Okay, how many are linearly independent? The answer is 3.
Okay.
Suppose if you treat them as column vectors, what could be the rank? The rank is again 3.
Yes, but the
It doesn't
columns are
change
4.
whether you take them as row vectors or column vectors. The rank is still 3. Is your doubt clear?
Yes, sir. Clear.
Okay.
Thank you.
Ishwar Rao?
Yes, sir. Sir, can I go to page number 122?
Yes.
So, here we got the, I mean, like, sir, example 6, sorry. So we got the relations like v2 is equal to 2v1 and v3 is equal to 3v1 and v4 is equal to 4v1, right?
Yes.
So can we add one more relation like v4 is equal to 2v2, or is it unnecessary?
You can do that also, but see here, finally what I want is, you can actually find this alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 equal to 0. You can actually find some alphas here such that this is 0.
Okay, sir.
Is that
so
okay?
if you were asked in the exams like what are the total number of relations out of these vectors? So we have to
No,
include
no, they'll not ask that way.
Okay, so
They'll not ask that way.
Okay, sir. It's clear. Thank you.
Yeah,
Deshpande.
Hello, sir. Sir,
Yes.
you wrote earlier that it belongs to R4, 121, I guess. Sir, what does that R4 signify, sir? R4 or R3?
See here, if I say x is a column vector which belongs to r power 3, that means x is in the form like this.
Okay, sir.
Suppose if I say x is a row vector which is belonging to r power 4.
Yes, sir.
Right, I'm saying row vector now. Row vector, then you're supposed to write like this. There are 4 components like this.
Okay, sir.
Is that okay?
Yes, sir. Sir, and
So he will clearly specify whether they are row vectors or column vectors.
Okay, sir. Sir, one fifth example, sir. Sir, where here you come to know that there are 3 linearly dependent vector and one is independent, sir.
Read that properly.
Sorry, sir. I told rank indicates 3 linearly independent and one is linearly dependent. So
Yes.
from the eigenvalues, can we make that the columns which contains eigenvalues are linearly
From
independent?
where you are bringing the discussion of eigenvalues? Did I ever take the
No,
word
sir,
called
not eigen. Sorry, sir. I was telling about the pivot elements, sir. Sir, if the columns contain the pivot elements, then they are linearly independent.
You can treat like that, but there is no rule like that. Okay, you can, any 3 would be linearly independent actually.
Okay, sir.
So there is no rule as such. Okay.
Yes, sir. I was confused, sir. Sorry.
There are many raise hands. Okay, I can't take this many doubts actually at this point of time because I have to complete the syllabus. Na, that is, see, it's like, yes. What is your doubt?
Yes, sir. Like if you have 4 column vectors, as you have discussed here, and the value is different, but whatever the value is, we will be getting a matrix with determinant with 3 rank, right? So
See,
What are
wait. First, just tell me your doubt clearly. Yeah, what you want? There are 4 vectors you are saying?
Yes, there are 4 vectors. 4
4
column
column
vectors.
vectors. Give me those column vectors.
Sir, whatever the value be, sir, just like if 1 0 0, 2 0 1, 2 0 3,
Okay.
1 1 1.
Okay. What you want to know?
So when we use this determinant approach, we will
First
be
of all,
getting.
you cannot use the determinant approach because V1, V2, V3, V4, when you combine and form a matrix, it's not a square matrix.
Yes, sir. So in these sort of questions, we cannot use this determinant approach.
In such case, I'm clearly saying that use rank approach, na?
That is what I am asking, sir. That is,
That's what is
the rank will be
explained.
3, right?
That's what is explained here. Find rank. The rank may or may not be 3. You have to first convert that to row echelon form.
Sir, anyways, the rank will not be 4, right? So
It may not
will
be 4, but first you
so
need to
it will
convert
be.
this to row echelon form.
Yeah.
So it can be 3, it can be 2, or it can be 1. So it can be anything. First find the row echelon form and then comment about the rank.
Sir, if it only comes 4 only, we can say that it is dependent, right? Independent, right?
Yes, but it's not possible here. That means for sure they are linearly dependent.
So whatever the values be, they will be always be dependent, right?
Yes.
Okay, that is matter. Thanks.
Okay. See here, my dear students, I can't take the doubts right now. So what I can do is I'll lower all the hands and I'll try to take at the break time, because this is not the right way to like handle the things. Okay. So it's like today I need to complete the syllabus. Once I complete the syllabus, I can go ahead with the doubts. If you have doubts, you write it on a paper. Once the entire class is over, I will take the doubts. So one nice thing that happened now was I made a mistake here. One of the student has identified and he immediately said. So that was one nice thing that happened in this doubt session. I'm very happy for that. Okay. So let me continue with my discussion now. I can't take any more doubts. So I have limited time. So let me go ahead. Once my syllabus gets over, I can sit along with you. Okay. So let me go ahead with my next topic. The next topic is about eigenvalues and eigenvectors. The next topic is about eigenvalues and eigenvectors. Before I teach you what are eigenvalues and eigenvectors, I just want to do one small activity. That activity will enhance your understanding skill. Okay. Let's do that activity. Everyone, you mute your mics. Once your doubt is over, please mute that so that there won't be any disturbance. Now, what is that activity? He says you to consider a vector called X. He defines a matrix called A. And then he says you to find AX when theta is 45 and 90 degrees. A very, very simple activity. So before doing this activity, what I would like to do is here, I would draw the coordinate axis. I would like to mark this vector that is 1, 1 somewhere here. So this is the point called 1, 1. This is origin. If you join this two, you get the vector called X. What is he asking? He's asking you to find AX. So let me take theta as 45 degrees. Let me find AX. So what could be A? A is 1 by root 2. This is A and X is 1, 1. Let's multiply them. This row into this column will give me 0. This row into this column will give me 1 by root 2 plus 1 by root 2, 2 by root 2, which is root 2. I just want to mark this vector here. So this is on y-axis actually. This is 0 root 2. If you join this with this origin, you get a new vector like this. So this is that vector. Now, second bit I want to find. That is when theta is 90 degrees. So what would be AX? Let me first write entries of A. Cos 90 is 0. Sin 90 is 1. This is row, this is column. This is row, this is column. This into this will give me 1. So where does this point lie? This is here. Now, this is a vector which is like this. Let's see some interesting points. The interesting points are the length of this vector is root 2. The length of this vector is also root 2. The length of this vector is also root 2. The other interesting aspects is, if you look at what is the angle between these two, the angle between these two is 45 degrees. If you look at the other angle, if you look at this, it's very clear that it is 90 degrees. Okay, so what I can say is, if this is x1, suppose if this is, let's say, x2, clearly x1 and x2 are perpendicular to each other. Perpendicular to each other. Few more observations I just want to tell you. Where did we start? We started with a vector called x. We started with a vector called x. When I put theta as 45, when I put, okay, yeah, I hope this is clear. So when I put theta as 45, I get a new vector that is 0 root 2. It looks as if the original vector got rotated in anti-clockwise direction by 45 degrees. If you put theta as 90 degrees and you find AX, you get a new vector. If you try to draw that, it looks as if the original vector got rotated in the anti-clockwise direction by 90 degrees. That means, in general, what is happening is, if you have a vector called x and there is a matrix called A, if you multiply A with x, you get a new vector. That new vector is simply rotating the original vector x by an angle theta in anti-clockwise direction. So here I just want to say that A is acting like what? It is acting like a rotation matrix. A is acting like rotation matrix. Is it changing the length of the vector? The length of the vector, it's not changing, because all the three vectors have the same length, that is root 2. All the three vectors have same length, that is root 2. What is changing is, right, the angle. Suppose if you look at this, the angle made by this vector with x-axis is 45. The angle made by this red vector with x-axis, positive x-axis, is 90 degrees. The angle made by this blue vector with x-axis is 135 degrees, right? So clearly A in this question is acting like what? A rotation matrix. Okay, so I just want to highlight the same point. A, that is this matrix, is rotating the x vector by an angle theta in anti-clockwise direction. I would like to add one more point. when you have a vector called X, when you have a matrix that is this, so have a look at this. Let's say A is n cross n. It's multiplied with X, which is X cross 1. So this is something like linear transformation. Linear transformation by A. So when you multiply A with X, you get a resultant vector. So what is this whole process called? This is called as linear transformation. In the earlier example, the transformation that happened was rotation. Now you can have something like this. The transformation can be something like stretching the vector X. The transformation can be something like shrinking the vector X. The transformation can be something like reflecting X about some axis. There are many transformations possible. Among them, I'm going to present the ones which are related to eigenvalues and eigenvectors. Okay, so whenever you see X as a vector, A is a matrix. Now when you multiply A and X, so this is termed as what? Linear transformation by A on what? On X. Right, when you have a vector called X and when you multiply it with A, you get a resultant vector. Now this whole process is called what? Linear transformation by A on X. Let's continue this discussion. Right, after some time, what I'll do is I'll be in a situation where there are two vectors. One is a vector whose elements are 1, 1, another vector whose elements are -1, 1. At that time, I'll ask, what is the angle between these two vectors? Right, so clearly the angle between these two vectors, that is 1, 1 and -1, 1, is 90 degrees. Right, after some time I'll ask that. You should be in a position to answer it. Let me now talk about introduction to eigenvalues and eigenvectors. So for that, I just need some support from you people, right? So I'll invite few students, ask their opinion. For example, let's talk to, so who was the one who identified the mistake? Vamshi Krishna. Let's ask Vamshi Krishna. Vamshi Krishna, are you there?
Yes.
Vamshi Krishna, I hope you have understood the transformation here. Did you understand what's happening here?
Yes, sir.
Okay. Now, Vamshi Krishna, just simple questions I'll ask. Try to answer that to the class. Okay. Do you see a vector here?
Yes, sir.
Which is called as X?
Yes.
Right. There's a vector called X now.
Yes, sir.
Can you tell me what's the meaning of 2X?
The length of the vector got increased by twice, like twice the length of first vector.
So earlier, if it was, let's say, X length, now it is twice of that.
Yes.
Correct? Okay, nice. Vamsi, is X and 2X in the same direction?
Yes, sir.
Right. X and 2X is in the same direction. I just write stretching the vector X by factor 2, I'll write stretching. Let me use another sketch here. Stretching X by what? By factor 2, correct?
Yes.
What about the direction?
Same direction.
Same direction.
In the same.
Okay, I'll not write that because it's in the same direction. Now try to understand this. What is this saying?
Shrinkage of.
You are just shrinking the vector X, na?
Yes, sir.
So I'll write that shrinking X by factor 2 again. Because I've used the word shrink, that means you will definitely decrease, na?
Yes.
What is the direction?
Same direction as earlier.
Right, in the same direction. Nice. Now come back to this one.
The same magnitude but with 180 degrees direction.
Yes. Now clearly earlier X was pointing like this. Now -X is pointing in the opposite direction, correct?
Yes.
So can I say that orientation has been changed?
Yes, sir.
Orientation. When I say orientation, that means the direction. Orientation is changed. What about this?
Stretching and the orientation is also changed.
Yes, stretching as well as orientation is also changed. So I'll just write stretching by 2, stretching by factor 2. Okay, by factor 2. Also, the orientation is changed.
Yes.
Now, what about this shrinking by factor 2? Is the orientation also changed?
Yes.
There was one GATE question which appeared in GATE 2021 like this. Okay, they gave a vector. I'll just try to put that. Okay, just look at this. Now you don't have that scalar. Instead of that scalar, I have put a lambda. Can you tell me what does lambda x indicate?
Stretching or shrinking by lambda times.
Right. So it will depend on like what is the value of lambda. But I can say that it's like a scalar multiple of the vector x, correct?
Yes, sir.
And suppose if lambda is positive,
There's
lambda is
no
positive, then
orientation.
lambda x is in the direction of x only.
Yes.
If lambda is negative,
it's oriented by 180, like orientation.
Yes. Or you can simply say now the direction is exactly opposite that of x, correct?
Yes. Yes.
Now finally you tell me your comment. What does lambda x indicate?
In stretching or shrinking of the vector in the same direction, like by a factor of lambda.
Yes. Suppose if lambda is positive, it will either indicate stretch or shrink. If lambda is negative, it will also indicate stretch or shrink. Apart from that, orientation will also be changed.
Yes.
Correct? Is there any doubt in this?
No.
No doubt. If you have understood this, then you people will definitely understand what is eigenvalue and eigenvector problem. Okay. So now let me introduce. See, I haven't said you anything about eigenvalue and eigenvector. I have created some background. Let me now talk about eigenvalue and eigenvector problem. Okay, so look at this. I have a matrix called A, which is an n cross n matrix. I have a vector called x, which is n cross 1. Now I have a scalar called lambda, and then I'm multiplying that with this. So if you understand this, what is this saying? You know, on one side, there is a scalar that is multiplied to x. On one side, there is a scalar that is multiplied to x. On the other side, there is a matrix that is multiplied to x. And we are putting a equality between them. That means what? Lambda x indicates either the stretch or the shrink. Suppose if lambda is negative, it will also indicate the change in orientation. What I want matrix A to do the same transformation as that of lambda. That means the matrix A should also either stretch or shrink x. The matrix A should also stretch or shrink x in the direction of x, and that factor must be lambda. Is that possible? Is that possible? I'll again repeat the problem. I have a vector called x. I have a scalar called lambda. I have a matrix called A. So what I'm doing is I'm first looking at lambda x. What does lambda x mean? Lambda x means that you are either stretching it or shrinking it. If lambda is negative, you are also changing the orientation. What I want is I want A to do the same thing on x. That means A should also stretch, shrink, or sometimes may change the orientation. But here the killer point is on one side there is a scalar. On the other side there is a matrix. Is it possible to find such lambda and x which satisfy Ax equal to lambda x? The answer is absolutely yes. You can find lambda and x such that Ax is equal to lambda x. How is that possible? I would like to tell you people now. Right? I have put the problem in front of you. Now I'm going to talk about its solution. Have a look at it. I would like to bring lambda x on the other side. If you bring lambda x on the other side, then what is left over is a zero vector. I would like to take x common. So if I write like this, it is meaningless because A is a matrix, lambda is a scalar. You cannot add matrix and a scalar. So to balance this, I'll put I here. So if you take x out, what you get is this times x must be what? 0. Now, this is in the form of bx equal to 0. Now this bx equal to 0 represents system of homogeneous equations. System of homogeneous equations. Now, I would like to go back here. The vectors that I have considered, the vector I have considered is x here. By default, in this discussion, x must be non-zero, right? By default, x must be what? Non-zero. Now you might be asking, sir, why should x be non-zero? X should be non-zero because if it is non-zero, only then you can actually stretch it, shrink it. If it is a zero vector, you cannot stretch a zero vector, you cannot shrink a zero vector. Lambda x will always be what? 0 only. So in this definition, right, in this problem formulation, I'm making sure that x is always what? A non-zero vector. Now what are you asking? You're asking, can you give me a value lambda, which is a scalar, and a vector called x, which is a non-zero vector, such that ax is equal to lambda x? So now, how do you find that? The answer is very simple. There is a system like this, that is a minus lambda times x equal to 0, which represents system of homogeneous equations. What we want is, we want non-trivial solution. Now, why do we want non-trivial solution? Non-trivial solution will only give you a non-zero vector. Okay, so this is like what? Bx equal to 0 form. Bx equal to 0 represents homogeneous equation. We want our eigenvector, that is vector x, to be non-zero. For that, what we want is, we want non-trivial solution. For that, what happens is, rank of a minus lambda I must be less than n. Non-trivial solution is possible only when rank of a minus lambda is less than n. When you say rank of a matrix is less than its order, when you say rank is less than its order, it means that its determinant must go to 0. Its determinant must go to 0. This is called as, the equation that you wrote, the condition that you wrote is called characteristic equation. Characteristic equation. Okay, I'm trying to justify each and every step that I'm writing. Okay, where did we start? We started with, we are finding a scalar called lambda, a vector called x, such that ax should be equal to what? Lambda x. We are searching for a vector called x, scalar called lambda, such that ax must be lambda x. Ax must be lambda x. So bring lambda x on the other side. Take the common. If you take x common, then what you get is a minus lambda times x equal to 0. Now this whole thing resembles like what? Bx equal to 0 form. Bx equal to 0 represents system of homogeneous equations, and very clear that the eigenvector, that is x, must be non-zero. That means what? We are actually searching for a non-trivial solution. Non-trivial solution is possible only when rank of this A minus lambda is less than n. So when you say rank is less than n, it must be a singular matrix. Singular matrix means the determinant must go to 0, right? Right. So now, how do you find eigenvalues and eigenvectors? I'll explain you. So I hope you people have understood this. Shaurya Chakra, you seem to have some doubt. Yash, are you following?
So page number 135, I had a doubt.
Yes, what is your doubt?
Sorry, sir, 131.
Is it related to eigenvalue and eigenvector?
Yes, sir. Sir, 131.
Yes.
Sir, here you wrote clearly x1 and x2 are perpendicular to each other, but sir, x1 and x2 have an angle of 45 degrees.
Wait, x, sorry.
Oh, yes, sir. Done.
Sorry, x. Actually, I said, when I was saying, I was citing this and this actually. Okay, the blue one.
Yes,
okay,
sir.
so
Actually, sir, when you wrote, I got confused. So no problem.
Yeah. Yash Saxena, did you understand this eigenvalue and eigenvector problem formulation?
Yes, sir.
Okay. Let me go through a few more points. I just want to interact with few students. Yash, can you read this?
Sure, sir. So for a n cross n matrix A, scalars lambda and vectors x n cross 1 not equal to 0, satisfying Ax equal to lambda x are called eigenvalues and eigenvectors of A respectively. And any such pair lambda comma x is called eigenpair for A.
So one important point, Yash, the x vector is called what? Eigenvector, and it has to be what? Non-zero.
Yes, sir.
Okay. So lambda and x are called what here? Eigenpair. Next point you read.
Geometrically, Ax equals to lambda x says that under transformation by A, eigenvectors experience only changes in magnitude or the orientation.
Is that also clear?
Yes, sir.
Now, when you multiply A with x, you get lambda x, na?
Yes, sir.
So what does lambda x mean? Lambda x is simply like you are changing. You are stretching it or shrinking it. And if at all lambda is negative, you are also changing its orientation. That's what is mentioned there. Next point you read.
The eigenvalue lambda is simply the amount of stretch or shrink to which the eigenvector is subjected when transformed by A.
Yes, it's the amount of stretch or the shrink, correct?
Yes, sir.
Next.
The characteristic equation for A is determinant of A minus lambda equals to 0.
I pointed out that also, na?
Yes, sir.
Determinant of A minus lambda equal to 0 is called characteristic equation. Very, very important. Okay.
Yes. The eigenvalues of A are the solutions of the characteristic equation or equivalently the roots of the characteristic polynomial.
Yeah. So if you solve this equation, you get lambda values actually. Okay. If you solve this, you get lambda values. So whatever roots you get, those are nothing but your eigenvalues. Okay. Now at this point of time, there would be a lot of confusion. Like, how do we find lambda or how do we find x? To avoid that confusion, I'll put two examples in front of you. Are you ready? Yes, are you ready?
Yes, sir.
My dear students, are you ready? Right. So what we will do is we will do some examples. I need some support from you people. Okay. So since I took Yash, I'll talk to another student. Whom shall I talk? I'll just take some support from them. Debadish, are you there?
Yes, sir. I'm.
Yeah. Debadish, have you followed this?
Yes, sir.
So most of the students by now might be having some doubts. Sir, how do we actually find that lambda or how do we find that x? Okay, so let me try to clarify that. Can you read this question, Debadish?
Yes, sir. Find the eigenvalues and the eigenvectors of the following matrix. The matrix is given as A equal to 3, 2, 1, 2.
I'll be solving two examples.
Okay.
Let me tell you one point very clearly. Whatever analysis I'm going to do now, we will not do that in our GATE exam. Okay. In the GATE exam, we will have some elegant ways of handling the questions. Okay, so let's see what is this procedure about. First step is write the characteristic equation. What is characteristic equation? Determinant of a minus lambda I equal to 0. Can you create a minus lambda I matrix for me?
Yes, sir.
So do you know how does I look like? I is nothing but the identity matrix multiplied with
Oh.
lambda.
Yes.
So only the principal diagonal elements change. That is 3 minus lambda, 2, 1, 2 minus lambda. Correct?
Yes, sir.
So now let's write the determinant of a minus lambda I. The determinant is 3 minus lambda into 2 minus lambda minus 2 equal to 0. Let me simplify this. When I simplify, I get lambda square minus 5 lambda. This is plus 6 minus 2 plus 4. Am I right, Devadish?
Yes, sir. Yes.
Can you give me the roots here?
Yes, sir. We can write 5 lambda as minus 4 lambda minus 1 lambda. So
I see that it is 1 comma 4.
Yes, sir. 1 comma 4. Yes.
Right. At this
Yes.
point of time, Devadish, I'll
Yes,
just ask you a few questions, Devadish. Okay.
Okay. Okay.
What are the eigen values that you have got?
So 1 and 4.
Can you add them?
Yes, sir. It's 5.
Adding them will give 5.
5. Yes.
So we usually say sum of eigenvalues here is 5, correct?
Yes, sir.
Look at matrix A. Tell me what is trace of A.
So it is 3 plus 2 equal to 5. Yes.
Correct. Okay.
5.
Now
Yes.
answer my question.
Okay.
What are the eigenvalues that you have got in this problem?
So 1 and 4.
What is their product?
So 4.
What is determinant of the matrix A?
So determinant of matrix is 6 minus 2 equal to 4. So,
now it happens that every time for any square matrix, the sum of the eigenvalues will always be equal to the trace of the matrix.
okay. Sir.
The product of the eigenvalues will always be equal to the determinant of the matrix.
Determinant of matrix.
We will list out all these properties, but I'm just highlighting that. Okay. Did we find the eigenvalues so far?
Yes, sir. We have.
Okay. Help me with few more calculations. I will say for lambda equal to 1, let's write a minus lambda I into x. Can you give me the matrix a minus lambda I when lambda is 1?
Yes, sir. It's 2, 2, 1, 1.
Into x. Na x means like unknown. So can I assume it as x1?
X1 and x2? Yes, yes.
So here you'll have 0, 0.
0, 0.
You are already aware of solving homogeneous equation, na?
Yes.
So we need to reduce this to row echelon form. That is R2 is R2 minus 1 by 2 times R1. Is that okay?
Yes, sir.
So 2, 2, 0,
0,
0,
0, 0.
times x1, x2 will give you 0, 0. If I read this row into this column, you know what I'm going to get?
Yes.
So let me write what I'm going to get is something like 2x1 plus 2x2 equal to 0. I get x1 equal to minus x2. If I say if x2 is 1, then what could be x1 here?
Minus 1.
Minus 1. So how does your eigenvector look?
1 minus, minus 1, 1. Yes.
Minus 1.
1.
Let's keep this aside. Devadish and all my dear students, we have put x2 as 1, na?
Yes.
I just want to say that if I change the value of x2, I get new x1, correct?
Yes, sir.
Like that, I can generate infinitely many eigenvectors for this eigenvalue called lambda equal to 1.
Yes, sir. We can generate.
Right. For a particular eigenvalue that is lambda equal to 1, we are able to generate infinitely many eigenvectors. Is that point clear?
Yes, sir.
Okay. So we are done with our first approach. Let's say for lambda equal to 4, can you give me what is a minus lambda I?
Yes, sir. -1, 2, 1, -2.
Okay. A minus lambda I times x equal to 0. So you say that it is -1,
-1, 2, 1,
-2 into x1, x2 should give me what? 0, 0. R2 is
R2 plus R1
plus R1. So with this, what I get is -1, 2, 0, 0 times x1, x2 equal to 0, 0. If I multiply this with this, what happens is I get minus x1 plus 2x2 equal to what? 0. This implies x1 is 2, x2. If x2 is 1, then what is x1? 2.
Sorry,
so
2.
What would be the eigenvector?
1, 2.
2, 1.
Okay, oh, yes.
Okay, so now we have got eigen values and their eigenvectors also we have got. Is that okay?
Yes.
Let's call this as E2. Let's call this one as E1. Okay, let me write E1, which is -1, 1, E2, 2, 1. Okay, in the exam, they'll ask, is E1, E2 linearly independent or not? Is E1, E2 linearly independent or not? So what I'll do is I'll check them like this. E1, E2, I'll form a matrix. -1, 1, 2, 1. What is the determinant here, Devadish?
-3. Yes.
This is clearly not equal to
0. So linearly independent. Yes.
Yes. Linearly independent. Not only about linearly independent, they'll also ask whether they are perpendicular to each other or not.
Yes, we can check the dot product. Yes.
Yes, very good. E1 transpose E2. So how does E1 transpose look like? It looks like this.
-1, 1, 2, 1.
How much is the dot product?
-2 plus 1, -1. So not
equal to 0.
Yes.
Okay. I hope you people have understood. Now I just want to tell that in this particular problem, it was a 2 cross 2 matrix. For a 2 cross 2 matrix, you'll have 2 eigenvalues, which are 1 and 4. For each eigenvalue, you can actually generate infinitely many eigenvectors. I have generated one eigenvector for lambda equal to 1. For lambda equal to 4 also I have generated one more eigenvector. I have also analyzed whether they are linearly independent or not. It turned out to be they are linearly independent, but they were not perpendicular to each other. Okay. Devadish, are you there?
Yes, sir.
I would like to take one more help from you. Can you just read it?
Yes, sir. Find the eigenvalues and eigenvectors of the following matrix: A equal to 3, 2, 2, 3.
Okay. I made some difference here. I just made small difference here. Is A symmetric?
Yes, sir.
A is symmetric. Because of this, you get few nice things actually. Okay. What's the first step, Devadish?
So A minus lambda I have to find.
I need to equate the determinant of A minus lambda I to
equal to 0. Yes.
So for that, I need A minus lambda I. So whenever you write A minus lambda, only the diagonal elements will change. So this is like 3 minus lambda, 2, 2, 3 minus lambda. I have to equate the determinant to 0. That is 3 minus lambda whole square minus 4 equal to 0. Let's see what would be the quadratic equation. The quadratic equation would be something like lambda square minus 6 lambda. 9 minus 4 is plus 5. Devadish, can you tell me what are the roots?
Yes, sir. 5 and 1.
Okay, 1 comma 5. Now again, let's verify. What is sum of eigenvalues?
So trace of the matrix A. Yes.
Shall we verify that? What is sum of the eigenvalues? 1 plus 5 is
6. 6. Yes.
Trace of A?
3 plus 3 equal to 6. Right?
What is product of eigenvalues?
So the equal to determinant of matrices. So here it is 5. 1 into 5 equal to 5. Yes.
The determinant is also 5, correct?
5. Yes, yes.
Okay. So now what next is, for lambda equal to 1, can you help me? What is a minus lambda I times x? Can you give me the entries of a minus lambda I when lambda is 1?
Yes, it is 2, 2, 2, 2. Yes, all in will be 2
into
x, x1, x2. Yes.
This is going to give us 0, 0. What would be the row operation that you are going to do?
R2 goes to R2 minus R1.
So with that, you get 2, 2, 0, 0, x1, x2, giving 0, 0. I hope this is clear.
Yes, sir.
Now let's try to read this into this. Okay, so what will this into this give us?
2x1 plus 2x2 equal to 0.
That means what? X1 is
x1
equal to
minus x2.
X1 is minus 1.
Minus.
Correct?
Yes.
So how does the eigenvector look?
Minus 1, 1.
Let's put this aside. And I will also, I'm trying to highlight that I can actually generate infinitely many eigenvectors. Is that okay?
Yes, sir. Yes.
Okay. Devadish.
Sir.
I'm asking you one critical question. Are you ready?
Yes, sir.
Can you tell me what is rank of a minus lambda I when lambda is 1?
A minus lambda when lambda equal to 1, sir. So it is 1.
Yeah, it is 1. Yes or no?
Yes.
Once again, I ask, what is rank of a minus lambda I when lambda is 1?
So it is 1.
Yeah, most of the students get confused. When I ask you clearly what's the rank of a minus lambda I, first you have to put lambda value into that, reduce that to row echelon form, and then comment about rank of a minus lambda I. What most of the students do, you know, they don't do this. They just find rank of a and return the answer. Is it different or not?
Yes, it is different because we have to find the row echelon form first.
Yes. Okay. So did we find the eigenvector?
Yes, sir. We have.
Yes. We are left over with one more eigenvector.
Yes.
So we'll say, let's put a heading called for lambda equal to what? 5, na? What was the other eigenvector eigenvalue got? 5 we got. Okay.
5.
So now I need a minus lambda I. A minus lambda I times x equal to 0. Let's see the entries of a minus lambda I. 3 minus 5 is minus 2.
Minus 2.
2, 2, minus 2.
Minus 2.
So what are the entries?
Minus 2, 2, 2, minus 2. Yes.
Times x1, x2 equal to 0, 0. Okay, so now I can say R2 is R2 plus R1. Yes. So what we get is minus 2, 2, 0, 0 times x1, x2 giving us 0, 0. So if I read it, it's like minus 2x1 plus 2x2 equal to 0. From this I get x1 equal to what? X2. So I'll just say if x2 is 1, then what is x1?
1. Yes.
The eigenvector, how does the eigenvector look?
1, 1.
1, 1. Few more observations. What are the two eigenvectors? The first eigenvector was minus 1, 1.
1.
The second eigenvector is 1,
1, 1.
Let's check whether they are linearly independent or not.
Yes.
What is the determinant?
Minus 2. Yes.
Not equal to 0. Therefore,
linearly independent.
Have you ever drawn a vector called 1, 1?
Sorry, sir.
Have you ever drawn a vector called 1, 1?
Yes.
My dear students, have you drawn vector called 1, 1? Yes. Have you also drawn a vector called minus 1, 1?
Yes. Yes.
Okay. E1 transpose E2. Let's find it. Minus 1 plus 1, which is 0. The dot product is 0. That means what? E1 and E2 are, yes, orthogonal to each other, are orthogonal to each other. The same is actually drawn here if you see it. See here, this is something like, let's say, E2. This is something like E1. The angle between them is 90 degrees or not? The angle between these two is 90 degrees, na? Yes or no?
Yes.
So
Yes.
through the geometry also I've shown that the angle between the two vectors is 90 degrees. Now the conclusion is, earlier, whatever eigenvectors you have got, they were not perpendicular. But here,
Yes.
the eigenvectors were perpendicular. That is because of the symmetric matrix.
Okay.
It is because of symmetric matrix.
Yes.
Okay. So right now, what I would like to tell is, in the exam, no one will do all these calculations. No one will do all these calculations. Okay. So there are some interesting properties of eigenvalues and eigenvectors. If one can understand the properties of eigenvalues and eigenvectors, you can avoid all these steps. Is that point clear, my dear students? Okay, so if you can learn the properties of eigenvalues and eigenvectors, you can avoid all this and you can answer the gate problems. One more last question, Devadish. Are you there? I'll leave you. You can relax now.
Yes, sir.
Devadish, are you there?
Yes, sir. Yes, I am.
Can you tell me what is rank of A minus lambda I when lambda is 1?
Lambda is 1, sir. Okay.
1. Okay.
Let me write.
Devadish, is this looking like some system called Bx equal to 0?
Yes, sir. Yes. Yes.
My question is, for a system called Bx equal to 0, how many linearly independent solutions are possible?
So it is equal to n minus r.
Perfect. I'll repeat it again. You should also repeat the answer. For a
Yes.
system called Bx equal to 0, how many linearly independent solutions are possible?
N minus r.
What is n?
So number of variables present.
What is r?
Rank of the matrix. Yes.
What is matrix here? Is it B?
Yes, sir. The matrix.
What is in the place of B?
So A minus lambda I. Yes.
Yes. Now the question is, they'll ask you in the exam, for a lambda that is lambda equal to 1, how many linearly independent eigenvectors are possible? The answer is very simple. It is n minus r.
N minus.
Okay? Where n stands for the number of variables. R stands for
rank of B.
Rank of which matrix?
A minus lambda.
Yes. Most of the students, they don't understand this. They feel R means always rank of A only. But
yes,
what kind of system are you talking about? Are you talking about A minus lambda times X equal to 0 or not?
Yes, sir. Yes, sir. That is equivalent to B. We are talking. Yes.
I tried to give you one overview of what is going to be discussed next. Okay. The next discussion would be about eigenvalues and eigenvectors properties, where you need not do all these calculations. Just by understanding the properties, you can answer the questions. At this point, I need a 10-minute break. I'll come back by 6:15. 6:15 to 6:30, I'll handle the doubts. You can also take a break, come back by 6:15. So I'll write the same thing on the screen. Once I come back, I'll take the doubts. Yukta, what is your doubt?
Sir, my doubt is from last class, sir.
Yeah.
Sir, in determinants, you gave one sentence sir, about minor determinant and submatrix.
Okay.
Get that statement, sir. Can I read the statement, sir?
Yeah, you can read that statement.
Minor determinant of A n cross n is defined to be the determinant of any k cross k submatrix of A.
Oh, you are, reading something else?
Last sentence, slide you are showing.
Okay, this one are you reading?
Yes, sir.
Yeah, so what is this saying? A minor, okay, minor determinant. So this is different from determinant. So I'm talking about a minor determinant of M cross N is defined to be the determinant of any K cross K sub matrix of A. What is your doubt in this? Hello?
What is the difference between minor and submatrix, sir?
See, minor refers to a determinant, okay? Hello?
Okay, sir.
Minor, whenever I use the word called minor, it means determinant. Okay, of what matrix? Of some K cross K submatrix. It looks like you are confused with the terminology. Minor means it's a determinant of a submatrix.
Then it should be of M cross and submatrix.
See, it's a suppose you have 3 cross 4. A is a 3 cross 4 matrix. So you deleted one column, you will get 3 cross 3 matrix, na? I'm talking about this determinant of this 3 cross 3. That is called as a minor.
Minor should be always square, like square.
Minor means what? It's a determinant of some submatrix. Is that clear?
Yes, sir.
Yeah.
Sir, I have one more doubt, sir. So can we apply the row operations given for determinants for also columns, sir?
Whatever row operations I taught you, if you do the column operations, again, the determinant changes by the same. Suppose you interchange the columns, you get a minus sign. If you do type 3 column operations, the determinants are unchanged.
Yes, sir. Same.
You can do column operations also, but while solving system of linear equations, don't do column operations.
When finding the determinant, we can use the
column operations also.
Last statement you said, sir, before break.
You speak loudly. Actually, I'm unable to hear you. You put your mic close to you. Yeah, what is your doubt?
The last statement you said, sir, even any 1, 1 and minus 1, 1 are orthogonal to each other.
Yes.
That means you're saying that like lambda x can also do rotational operations, rotation transformations, not only efficiency.
See, what we have got 2 eigenvectors, right?
Yes, sir.
First eigenvector is associated with lambda equal to 1. The second one is associated with, let's say, lambda equal to 5. If you try to draw them, the angle between them would be 90 degrees.
Yes.
Okay. See, there is no rotation here. We are just drawing 2 vectors and seeing what is the angle between them.
You can do only this like lengthwise transformations by lambda x.
See, in the second example, I have calculated the eigenvectors. I found one interesting aspect, that is the 2 eigenvectors are actually perpendicular to each other. Okay. Hello.
Yes, sir.
Yeah, so you need to exactly tell your doubt. You are like confused while asking your doubt. Can you repeat your doubt again?
Can I ask in Telugu, sir?
Yeah, you can ask me in Telugu.
ఇప్పుడు అక్కడ రెండు ఇప్పుడు పర్పెండిక్యులర్ అని వస్తున్నాయి కాబట్టి అది రొటేషనల్ ఆపరేషన్ కూడా ట్రాన్స్ఫర్మేషన్ కూడా చేస్తుందని చెప్తున్నాను సార్.
అసలు ఇక్కడ రొటేషన్ కి సంబంధం లేదమ్మా. మనం రెండు ఐగన్ వెక్టర్స్ కనుక్కొని దాని యాంగిల్ ఎంత ఉందో చెక్ చేస్తున్నాం అంతే. ఓకేనా? Okay. Yeah. Yash, what is your doubt?
Sir, in this same thing, so when a matrix is symmetric, then we'll have orthogonal eigenvalues. Sir, eigenvectors. Sir, we know that we can have infinite eigenvectors for the eigenvalues.
So it's like I'm taking the eigenvector, one of the eigenvector of lambda 1 and another eigenvector from, I'm taking the eigenvectors generated from different eigenvalues actually.
So sir, if we take any two of those vectors, they'll be perpendicular, but not from the same eigenvalue.
Yes.
Okay.
If you take from the same eigenvalue, they'll be in the same direction. That means they will be parallel actually.
Okay, sir. Got it, sir. And sir, one more doubt. Sir, you told that rank of a matrix will be the number of linearly independent vectors.
Number of linearly independent columns or rows of A.
Yes, sir. So, sir, if there are four vectors, column vectors like V1, V2, V3, and V4, and the rank is 2, that means there are two linearly independent vectors. Sir,
there are
they
two
can
linearly independent columns. You can also see there are two linearly independent rows also.
But sir, V1, V2, V3, and V4, if they are columns, then they'll be.
Hello. Continue.
Sir,
what is your doubt?
Sir, V1, V2, V3, and V4 are column vectors. And we have to check whether they are linearly independent or not. And we got the rank to be 2. That means there are two linearly independent vectors.
First comment is the given set is dependent set. In
yes,
that
sir.
dependent set, there are two linearly independent vectors. That's it.
Yes, sir. Sir, they can be any two, or we can find out. Like by observation, we can do, but they can be any two, like
Any two,
V1,
yes.
V4, and V3, V2, and all.
Yes.
Okay, sir.
Daman?
Hello, sir. Can you hear me?
Yes.
Sir, in this example only, actually, eigenvectors corresponding to distinct eigenvalues are always orthogonal now, sir.
Eigenvectors corresponding to distinct eigenvalues may not be orthogonal all the time. Example 1, if you look, eigenvectors have generated, but they were not perpendicular. You can check it.
Okay, they're only orthogonal for symmetric matrices.
Symmetric matrices, yes.
Are they orthogonal for skew symmetric also?
No, we can't say.
Okay, sir. That's it.
Krishna Vamsi?
Sir.
Your
Sir,
doubt?
page number 132, sir.
Okay.
Oh, sorry, sir, 133, I think. Their coordinate system. Yes. Sir, here generally we consider x vector as a in 2D coordinate system, no, sir.
You can extend that to n coordinate system, n dimensional coordinate system also.
Yes, sir.
Whatever analysis we are doing, you can extend that to n dimensional, but n dimensional I cannot draw. So I have drawn the simplest one, that is 2 dimensional.
Sir, in that sense, when we are doing examples for lambda equal to 1 or lambda equal to 5, their x value will be greater. For example, we took 5. Then A matrix will also be n into n. That means 5 into 5. Then the complex, it will be complex, sir. Is there any easy way to solve that?
No. What is your question again? You are confusing. You are saying.
Oh, sorry, sir.
Lambda is equal to 5. Lambda equal to 5 is an eigenvalue. How is this related to order?
No, sir. Actually, here x vector is of n into 1 order, no, sir.
Okay, I got it. You are saying like x vector is in the 5 dimension.
Yes,
how
sir.
do we find eigenvalues? That is what we are going to discuss next.
Okay, sir.
That's what I said now before the break. There are elegant ways of finding eigenvalues and eigenvectors. Let's discuss them.
Okay, sir. Thanks.
Mahati. What is your doubt, Mahati?
Sir, can you hear me?
What is your doubt? Yes, I can hear.
Sir, page number 114.
114.
Sir, in this question, if you put k equal to -2, we get infinite solution.
Louder, yeah. K equal to?
-2.
If you want to put k equal to -2,
we will get infinite solutions.
You get only for k equal to 0 and 2. You are mistaken. For k equal to -2, you will not get it. You please verify your calculations.
I got that value also equal to 0.
What?
When we put k equal to -2, I got that value also 0.
Okay, you please verify that. If you put only two values are there for which you get infinitely many solutions. One is case 0 and case 2. Please verify your calculations.
Okay. Sir, one more doubt. Sir, overdetermined system, what is it? Overdetermined.
Overdetermined means something like, suppose you have more equations and less number of unknowns. You have more equations and less number of unknowns. That is called overdetermined system.
Sir, can we comment on the solutions?
We can't comment anything about that unless until you give me the coefficient matrix, you give me that B, I'll work it out, reduce that to row echelon form. There is a question on that in the GATE exam which was wrong.
Okay.
Yeah.
Sir, if variables are more than the equation.
If
variables are more than the equation.
Under determined system, even in that also we can't comment anything.
Okay. Sir, and eigenvectors are always linearly independent. Can we comment on?
We will talk more about the linear independence of the eigenvectors now. Okay, don't worry about that. Can you repeat your doubt again?
Can we say eigenvectors are always linearly independent?
Eigenvectors corresponding to distinct eigenvalues.
Okay, sir.
They are always linearly independent.
Okay, sir.
Thanos, what is your doubt? Venkatamohan Vamsi, what is your doubt?
So page number 131, sir. Sorry, 121, sir, not 131. Sorry. Sir, in this, someone said that there are row vectors. V1, V2, V3 are row vectors. Why don't we write in a column, sir, those V1, V2, V3?
See, you write it like column, row, it doesn't matter. Okay.
But
if vectors are given to you, they're asking you whether they are linearly independent or not, find their rank.
So, but how can we say the relation between V1, V2 and V3, sir? Those are row vectors.
Again, the same concept, na? Alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. But this time, earlier they were like this. Now they are like this. What's the difference? There is no difference, na?
Okay, sir.
Again, you need to search for alpha 1, alpha 2, alpha 3, such that alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 is 0.
Okay, sir.
Yeah.
And sir, one more thing. So can you please repeat that V1, V2, V3 belongs to R power 4? What does it mean, R power 4?
Suppose if I say V1 is a column vector belonging to R power 4. Okay.
Okay, sir.
It means V1 is in this form.
Okay, sir.
Is that okay? It has got 4 components.
Okay, sir.
That's it.
Okay, sir. Thank you, sir.
So,
yes, Thano, Thomas, sorry.
So in page 140. So if this matrix 2, 2, 0, 0, in that final element is not 0, then the solution will be trivial now.
It will see here. We have put this in such a way that for sure you will get infinitely many solutions. You won't get that case because the determinant is 0. You refer to this.
Okay,
Clearly,
sir.
I made rank less than n. Then only I got that condition. Okay, so that case will not arise.
Okay, okay. Okay, sir. Thank you.
Pavitra. Last doubt. After this, we'll continue with the discussion. Pavitra, what is your doubt?
So page number 127. Sir, about this not in this page, sir. You have talked about the sum Sum after this one, the problem after this question. Yes, sir. In the sum, the last summary, you have told that V1, V2, etc. to Bn are linear independent. Can you explain this last two summaries?
See here, I have already created some examples. Look at this. V1, V2, V3, V4. Okay. Is the set dependent set? Yes.
Yes, sir.
Is the set dependent? Yes, it is dependent. Now take V1, V2, V3. Take only V1, V2, V3.
Yes, sir.
If you take V1, V2, V3, they are also dependent.
Yes, sir.
Okay. Now I'll take another example. Now take V1, V2, V3, V4 here.
Yes, sir.
This is also dependent. This is also dependent set. But when you take V1, V2, V3, they are actually linearly independent. If you take V1, V2, V3 only, they are actually independent.
Okay, sir.
That means if you have a dependent set and if you pick, let's say, some of the vectors, those like whatever, let's say there are total n vectors and you have taken only r of them, that r of vectors may or may not be linearly dependent.
Okay, sir.
That's what is written there.
But in case of linear independent, it will be always linearly independent
only. In the case of independent vectors, let's say there are n and you pick r, those r for sure are linearly independent.
Okay, okay, sir.
Okay. I'll take one more doubt and then this close this. Trivikram Reddy.
Hello, sir. Can you hear me?
Doubt? Yes.
Yes, sir. It's from previous class, sir.
Previous class, you can ask me at the end. Okay. Anything related to this discussion, it would be nice. Okay. I'll go to the Vaibhav Patel. Vaibhav Patel, what is your doubt?
Sir, 121, sir, page number.
Okay.
So that belongs to R to the power 3 and R to the power 4. Here you 3 rows and 4 columns. Sir.
What is your doubt?
Sir, X belongs to R to the power 3.
Huh.
Here 3 columns should be shown, no, sir? Or
you are not listening to the lecture properly. Here X belongs to R power 3. I said it's a column vector. So it will be like this 3 cross 1. Now in the next example, I said X belongs to R power 4. It's a row vector. So it will be in the form of 1 cross 4. Is that clear?
Yes, sir.
Okay.
Thank you.
Trivikram Reddy, tell me your doubt.
Hello, sir. You told that you will give solution for one particular problem, sir. That of IM plus AB equals to that of.
I'll upload that. Don't worry. Anyway, I gave you the one solution, easy solution. Now what I'll do is I'll upload the entire notes. Today I'll upload today's notes as well as entire linear algebra PDF. So you can find that in the entire notes. Okay.
Okay.
Yeah. So now let's continue this discussion. I'm lowering all the hands. Everyone mute yourself.
Sir, so in last class, you have given an homework of another sum, sir.
We will discuss that later. Now I'm running out of the time. Okay. We will discuss that at the end. Okay.
Okay, sir.
Okay. So now I would like to give you properties of eigenvalues and eigenvectors. Very, very important ones. Like you will definitely get a question based on these properties. Let's see what are those properties. The first property says the sum of the eigenvalues is equal to trace of the matrix. I have already discussed this. Like I verified with 2 problems. The product of eigenvalues is equal to the determinant of the matrix. I have verified this also. The third one, the eigenvalues of a triangular or diagonal matrix are its principal diagonal elements only. Most of the students mistake this. Okay, this particular property is applicable only to triangular diagonal matrices. If you are given, okay, if a matrix is given to you and it's a triangular matrix, you need not find the characteristic equation. Just the principal diagonal elements are the eigenvalues. Okay, now some stupid people, what they do is, okay, they just think too much. They'll take a matrix called A, they'll convert that to row echelon form, so it looks like a triangular matrix, and they'll claim that the principal diagonal elements are the eigenvalues. This will not work. Please understand that if you are given a triangular matrix or a diagonal matrix, the principal diagonal elements are the eigenvalues. If you are given any other matrix, then you are supposed to find the characteristic equation and then find the roots of the polynomial. Please take this as a serious warning. Most of the students get confused and they lose these marks. So please understand that. Next property says the eigenvalues of A and A transpose are same. A and A transpose have got same eigen values. We have got few more interesting properties. If lambda is an eigenvalue of a non-singular matrix, then the eigenvalue of A inverse is dash. The answer is very simple. So let me show you how do we find that. I'll write this reference, that is Ax equal to lambda x. I'll multiply A inverse on both sides. A inverse into A will give me I. So I into x is anyway x equal to lambda times A inverse x. I would like to send this the other side. In such case, this looks like A inverse x is equal to 1 by lambda times x. Now from this, the conclusion that I get is, for a matrix called A inverse, the eigenvalue is 1 by lambda. Very simple observation. It is 1 by lambda. Let's try to see what could be the eigenvalue of adjoint A. For that, what I would like to do is I'll write the reference again. That is A inverse x is 1 by lambda times x. What is A inverse? A inverse is adjoint A by det A times x equal to 1 by lambda times x. Since the discussion is about adjoint A, I'll just put adjoint A this side. I'll send det A on the other side. So this would be det A by lambda. So it's very clear that from this, for a matrix called adjoint A, the eigenvalue is det A by lambda. So here the answer is det A by lambda. So these are the properties of A inverse and adjoint A. If you know these properties, the advantage is, if they give you the eigenvalues of A and they ask you the eigenvalues of A inverse, you need not find the matrix A inverse. Simply take the reciprocal of the eigenvalues. Let's see the next one. If lambda is an eigenvalue of A and K is a scalar, then what? Okay. So see this discussion, very, very interesting one. Let's take the reference Ax equal to lambda x. I would like to write, or I would like to multiply A on both sides. This is A square x equal to lambda into, now if you look at this, Ax, instead of Ax, I can put lambda x. Instead of Ax, I can put lambda x, because the earlier equation says Ax is lambda x. So this is lambda x now. What we get is A square x is lambda square x. It's very clear that lambda square is eigenvalue of A square. Similarly, a very important property. Lambda power n is an eigenvalue of what? A power n. Using this, what happens is you need not find the matrix A power n. That's the advantage. You need not find the matrix A power n. You know the matrix A, find the eigenvalues of A, then lambda power n would be the eigenvalues of A power n. That's a nice property. So I would like to fill the first blank, that lambda power m is eigenvalue of A power m. K lambda, where k is a scalar, would be eigenvalue of the matrix called Ka. K plus lambda, I mean lambda plus k, lambda minus k, lambda plus k, lambda minus k would be eigenvalue of A plus ki. This would be eigenvalue of A minus ki. We will talk about the last property in the next page. The last property says A naught plus A1 lambda plus A2 lambda square is eigenvalue of, it's a very simple observation, eigenvalue of A naught into I plus A1 into A plus A2 into A square. A very important observation, right? So these are some of the properties of eigenvalues and eigenvectors. I would like to put few more properties in front of you. If you look at this, you assumed that x is a eigenvector of A. Interestingly, x is also eigenvector of A inverse. Interestingly, x is also the eigenvector of adjoint A. Interestingly, x is also the eigenvector of A square, A cube, A power n. That means the eigenvectors of A square, A cube, A power m, A inverse, adjoint A are all same as what? The eigenvectors of A. Okay, they have the same eigenvectors. So I'll just write look at one more property. A and A transpose may or may not have same eigenvectors. Okay, so these are some of the properties of eigenvalues and eigenvectors. I would like to discuss few more properties, right? All the properties which are very important for gate point of view, I would like to discuss them now. So let's go ahead. Now see this interesting one. A plus root B is an eigenvalue of real matrix A, then A minus root B is also other eigenvalue of matrix A. Okay, A plus root B eigenvalue of A, then A minus root B is also eigenvalue of A. But to apply this or to use this, you have to make sure that the entries of the A are real entries, real numbers. One more interesting property. A plus IB, where I stands for a I value is root minus 1. If A plus IB is one of the eigenvalue, for sure A minus IB is also one of the eigenvalue. Okay, that means they occur in conjugate pairs, provided the matrix that you are dealing is a real matrix. Okay, so these are few more properties of eigenvalues and eigenvectors. I've got few more properties here. The eigenvalues of symmetric Hermitian matrix are always real numbers. This particular property appeared in the gate many number of times. Okay, so this appeared in the gate many number of very important property. What is this saying? The eigenvalues of a symmetric or Hermitian matrix are always real numbers. When it comes to skew symmetric matrix or skew Hermitian matrix, they are either zero or purely imaginary. They are either zero or purely imaginary. Orthogonal matrices, unitary matrices. You know what are orthogonal matrices? You know what are unitary matrices? They have got their eigenvalues magnitude equal to 1. If you look at the eigenvalues of orthogonal matrix or unitary matrix, their magnitudes, the eigenvalues magnitudes is 1. The eigenvalues of nilpotent matrix are always 0. Okay, all the eigenvalues of nilpotent matrix are always 0. So these are the most important properties of eigenvalues and eigenvectors. Again, time to time, whenever I come across properties, I'll highlight them. While solving few problems, I'll teach you few more properties. So we will also highlight them. Now, next, this is what I was saying. Some of the students, I don't know why they get distracted. What they do is the following. I'll ask someone to read this. Okay. Naga Venkata Mohan Vamsi, are you there? Naga Venkata Mohan Vamsi, are you there?
Yes, sir.
Okay. You did not get the chance now for doubts. Okay. We will discuss that. Can you read this sentence?
Yes, sir. Common mistake made by students. For finding eigenvalues of A, they reduce A to row echelon form and say that the principal diagonal elements are eigenvalues of A.
So this is wrong actually. You should not do this. Okay. What you should not do, if a matrix A is given, don't reduce that to row echelon form. Don't look at the principal diagonal elements. Don't say that the principal diagonal elements are the eigenvalues. Okay. Vamsi Mohan.
Yes, sir.
What is the procedure for finding eigenvalues? Do you know?
Yes, sir.
What is the procedure?
So we need to find the characteristic equation A minus lambda I. And then we need to find the value of lambda. I mean,
yes.
we need to find eigenvalues.
So what you are saying is the reference is characteristic equation, correct?
Yes, sir.
But not the row echelon form. Don't try this. Okay. But for triangular matrices, for diagonal matrices, what are the eigenvalues?
Principal diagonal elements.
That is true only in the case of which matrix?
Triangular or diagonal matrix.
Any other matrix, if it is given, what you should do is don't reduce to row echelon form. Form the characteristic equation. That's the right procedure. Okay.
Okay, sir.
Okay, nice. So we are done with most of the important properties. Now we have some problems. I'll interact with the students. I'll take their opinion and then solve it. Okay. Though Naga Venkata Vamsi, can you read it?
Yes, sir. The minimum eigenvalue of the following matrix 3, 5, 2, 5, 12, 7, 2, 7, 5 is.
Okay. I'll give you the hints. Okay. I'll give you the hints. It's a 3x3 matrix. The usual procedure is find all the eigenvalues, see which is the minimum.
Okay, sir.
But that is going to take time. Find all the eigenvalues, see which is the minimum. That is going to take time. I just want to ask you one question. Okay. That is, look at the rows or columns, whatever you want. can you see any relation between the columns?
Yes, sir. It is symmetric matrix.
It is symmetric. Very good. Apart from symmetric, do you see any relationship between the columns? Okay, I'll make you answer that. What is 3 plus 2?
5, sir.
5 plus 7?
12.
2 plus 5?
7.
Can you see those elements sitting here?
Yes, sir.
That means, can I write something as C2?
C1 plus
C1,
C3.
Can I say C1, C2 and C3 are
Linearly dependent.
You got that point, na?
Yes, sir.
When they are linearly dependent, what is the determinant?
0, sir.
0. Do you have any property related to the determinant of a matrix and eigenvalues?
Sir.
I have a property. I'll tell you. That property is product of eigenvalues is the determinant of the matrix.
Yes, sir.
We concluded that the product is 0.
Yes, sir.
I mean, we concluded that the determinant is
Determinant
0.
is 0.
When the determinant is 0, one of the eigenvalue must be 0.
Yes, sir.
Okay, I'll write that note point. One of the eigenvalue must be
0.
Are you sure that one of the eigenvalue is 0 now?
Yes, sir.
Can you read the options?
0, 1, 2, and 3.
I'm sure that 0 is one of the eigenvalue and 0 also happens to be the minimum value in the options.
Okay, sir.
Okay, so the answer for this question is A. They ask this kind of questions in the exam. What is the property that I highlighted here? The product of eigenvalues is equal to what?
Determinant of that matrix.
And one more nice property. Whenever the determinant is 0, for sure, one of the eigenvalue must
be 0.
Yes, right? So I'll try to interact with the students. I'll give you one more question. As I could not deal with the doubts, I'll give you one more question.
Okay, sir.
Can you read this?
A real 4x4 matrix A satisfies the equation A square equals to I, where I is the 4x4 identity matrix. The positive eigenvalue of A is.
Okay. Is it dealing with 4 cross 4 matrix?
Yes, sir.
He gives that A square is I.
Equals to I.
How does this look like?
1 0 0 0 1 0 0 0 0 1 0 0 0 0 1.
Can you tell me the eigenvalues of A square?
So 1.
Eigenvalues of A square are all ones.
1, sir.
Okay. If lambda is eigenvalue of A,
okay, sir.
Then what can I say about A square?
Lambda square is the eigenvalue of A.
Lambda square is eigenvalue of
A square.
That means clearly lambda square is 1 in the problem.
Yes, sir.
Which implies lambda is
Plus or minus 1.
Now read the question again and try to give me the answer.
Sir, a real 4x4 matrix A satisfies the equation A square equals to I, where I is the 4x4 identity matrix. The positive eigenvalue of A is plus 1, sir.
Yes. So the answer for this question is 1. Okay. So
yes,
let me go to the next student. Akshay. Akshay, Ashish. Not
yes,
doubt, but I want to interact with you. Okay.
Okay, sir.
Can you read this and give your opinion about this question?
If A is equal to 8 minus 6 to
minus
No need
6.
to read all the elements. A is some matrix, let's say. Then
Yeah, then eigenvalues of A are it's symmetric.
Ashish,
Sir. Yeah.
Ashish, I want to ask you a few questions. Yeah, it's symmetric. You say symmetric matrix? Yes, okay. Can you tell me what is sum of eigenvalues, Ashish? Property?
Trace of A minus lambda I.
It is trace of A only, not trace of A
Okay,
minus
okay,
lambda.
okay,
It's
sir.
simply trace of A. What is product of eigenvalues, Ashish?
No, a product of all the PD.
Product of eigenvalues is simply the determinant of A, Ashish.
Okay, okay, determinant of A.
Okay.
Yes, sir.
Now, from the given problem, can you tell me what is trace of A?
Trace of A is 8 plus 7, 15 plus 3, 18.
18. From option A, add all the eigenvalues.
18, sir.
Okay, this can be the answer. From B, add all the eigenvalues.
Again 18.
This can also be the answer. Read C.
The rest are not 18.
So you can eliminate this.
Yes,
now, can you help me, Ashish? I'll wait for you. Can you find the determinant of this matrix? I'll wait. You take your time. Give me the determinant of this matrix.
Okay, sir.
Other students, just tell whether Ashish is right or not. He will be like giving the answer. Dinesh Venkatasai, I'll talk to you also. Just give me some time.
Sir, is it 0?
Yes, it is 0 actually. Okay.
Sir.
The determinant is 0.
Okay, sir.
What should be the product of eigenvalues?
Product of eigenvalue is oh, it's 0.
That means it should also be 0, na?
Yeah,
Yes or
yes,
no?
sir. Yes, sir.
Is A
Determinant.
eliminated now?
Yes, sir.
So what is left over? Only B.
Option B.
So what's the answer?
Option B, sir.
Yes. Will you help me with one more question? I just want to interact. See, through
Sure,
this
sure, sir.
interaction, what happens is I'll be in a position like I'll be like, okay, I'll feel okay, this the students are able to understand. Okay. So that is also required for a teacher.
Okay, sir.
I just want to know whether you are following or not. Okay, next question. Can you
Sir,
read this?
I had a small doubt. In last
will-
question, you said determinant is 0, then one of eigenvalue must be 0. So I didn't understand where that came from.
Okay, from where that came. We have a property saying that the determinant of a matrix is equal to the product of eigenvalues.
Okay, okay, sir.
The
I didn't know
determinant of
that.
a matrix
Okay,
and
sir.
a product of eigenvalues are same actually. So when you say determinant is 0, then product of eigenvalues should also be 0.
Oh, okay, sir. That
When
explains
product
this
of
problem.
eigenvalues
Also.
is 0, then one of the eigenvalue must be 0, na?
Yes, sir. Yes, sir. I understood that, sir.
Yeah. You help me with this problem, Ashish.
Eigenvector of the matrix 10 minus 4, 18 minus 12 is.
And 4 options are given, correct?
Yes, sir.
See, in the exam, what happens is they'll not give you a 2 cross 2. Instead of that, they may give you a 4 cross 4 or a 5 cross 5.
Okay,
Finding the eigenvalues and then finding the eigenvectors would be very, very time consuming. What you can do is you can go for a verification in this kind of problems. You can go for a verification. So what does this verification mean is I have a reference called ax equal to lambda x. Whichever option gives me ax to be lambda x, that would be the right answer. Okay. I'll help you how to do the verification. Let me say option A. So what is A? 10 minus 4. What is x?
X 1 minus 1.
Give me the product.
14 and 18 plus 12 is 30.
Suppose if 2 is common, let's say.
Yes,
What is
sir.
left over? 7?
7 and 15.
here you took AX. Here, are you getting lambda times the same X?
Not the same X, sir.
That means this is not the eigenvector.
Oh, okay, okay.
Okay, see, very, very important for exam point of view.
Sir, can't we use that sum of diagonal thing? I mean,
eigenvalues are not given, eigenvectors are given here.
oh, okay, okay, sir.
Yeah. Go for the next option. Help me with the next option verification.
That would be 20 minus 108.
20 minus 36.
Oh, okay, okay. 20 minus 36.
Next.
Minus 16 and 36 minus 12
108.
into 108.
How much?
72.
What
minus
is common
72.
in this two?
8. 8
If I
is
put
minus
minus
8.
8.
Yeah, minus
What
8 is
do you
common.
get?
2 and 6 is, yeah, 9.
9.
Hmm.
Okay, now observe this. Is this AX?
Yes, sir.
Is this looking like lambda times the same X?
Yes, sir.
That means this is the right answer for the question.
Yes, sir.
So this way you are actually avoiding finding the eigenvalues and eigenvectors. This is going to be very, very useful if the question deals with 4 cross 4 or 5 cross 5. Is that point clear?
Yes,
Even
sir.
with 3 cross 3 also. Now just to have some completeness, I'll also verify C. What is the eigenvector? 2, 3. How much is the product? Help me.
8 and
10,
no.
20 minus
20
8.
minus
Correct.
12,
Next.
8. And 36 minus 12 into 3 is 36, 0.
Is this anyway looking like lambda times the same X?
No, sir.
No. So that means this is eliminated. So what do you think is the answer here?
Option B, sir.
Similarly, you have to do for D also. Okay. So
Okay,
since
sir.
you people can do it, I'm just going to the next problem.
Okay, sir.
Okay. So let me talk to some other student here. Take their opinions, suggestions. So I was about to talk to some person. I forgot his name. Yeah, Venkatasai. Nice.
Yes, sir. Good evening, sir.
Venkatasai, are you following?
Yes, sir.
Okay. Venkatasai, look at this. Read it.
An eigenvector corresponding to the smallest eigenvalue of the matrix is
dash.
Yes.
Okay. Again, verification will work here. Verification. Venkatasai, I'll ask you a simple question. Answer this. There are numbers like 1, 2. First of all, tell me, is this matrix triangular matrix?
Yes, sir.
It's a triangular matrix.
Yes,
Upper
sir.
triangular matrix, correct?
Yes, sir.
What are the eigenvalues of upper triangular matrix? Eigenvalues of upper triangular matrix are the principal diagonal elements itself. Okay, so 1, 2, minus 1, 0. Are you there?
Yes, sir.
How many eigenvalues do you see on the screen?
So 4.
Among them, which is the smallest eigenvalue?
-1.
Why are you looking at smallest eigenvalue?
Sir, in the question it was asked about smallest eigenvalue of the matrix.
Very good. An eigenvector corresponding to the smallest eigenvalue. So smallest eigenvalue is minus lambda. Sorry, -1. So I'll write here. Smallest eigenvalue is -1. That means if you go for verification, AX should give you what?
Yes, sir.
Right. This is what you are supposed to get. Shall we go for verification?
Yes, sir.
Tell me what happens with option A. You put option A here, 1, 0, 0, 0 here. Try to multiply this with this. Tell me what could be AX.
Sir, AX would be 1, 0, 0, 0 itself.
Wait. 1,
0, 0, 0.
So what you have done is you have multiplied this with this, this with this, this with this. Am I right?
Yes, sir.
Is this looking like 1 times X?
Yes, sir.
1 times X. But are you looking at 1 times X or minus 1 times X?
Minus 1 times X.
No, this is wrong answer actually. Help me. So this is option A, by the way. Option B, let's look at. Option B is 1, 1, 0, 0. So please do me the verification. What would be AX?
It would be
this into this will give me 2 first of all.
2, yes, sir.
This into this will give you again 2.
2, sir. 0,
this
0.
Into this 0, 0. What is common?
Sir, 2 is common.
What is this giving me? 2 times X. But what I'm expecting?
Minus 1 into X.
So this is gone. Let's go for C. Let me write option C. That is 1, 0, 2, 0. Can you help me with the product? That is this row into this column.
Yes, 3.
Are you sure?
Yes. Sorry, sir.
Once again.
No, sir. No, sir. Minus 1.
AX is minus 1 as the first element. Next element.
0.
Next element.
Sir.
This into this. This row into this column.
0.
This row into this column is not 0. One more chance I'll give you.
Minus 2, sir. Sorry. I was thinking about second round.
Yeah, last element, please.
0, sir.
Okay, what is common in all this?
So, minus 1.
Okay, minus 1. So if I write minus 1, what is left over?
1, 0, 2, 0.
2, 0. Now, you see that X is 1, 0, 2, 0. AX gave you minus of that, correct?
Yes, sir.
That means this is the right answer.
Yes, sir.
Is that clear?
Yeah, yes, sir. I'm clear, sir.
Yeah. Yeah. So we will talk to Muhammad Ali now. Muhammad.
Yes, sir.
Are you following?
Sir, how did you multiply like AX? Which row multiply by which column, sir? I'm not getting
it. Shall we do the option A first? Shall we check?
Yes, sir. Yes, sir.
This row into this column will be this first element.
Oh, this row.
This row into this column would be the first element.
Okay.
Or for example, let's take option C, Mohammed.
Yes, sir.
The first row into this, how much you get? 1 into 1, 1 into 0, minus 1 into 2, 2 into 0. Add it.
Okay. Yes, sir.
You will get minus 1.
Yes, sir.
Like that, you have to complete this. So second row into again this vector, third row into this, fourth row into this. Is that okay?
Okay.
Okay. So hope you are following this.
Yes, sir.
Yeah. You also try to interact with me. Read this.
Hello.
Yeah. You read this question. We will I'll see I'll take your ideas here. Read it.
Okay. If 2 minus 2 1 transpose is an eigenvector of the matrix A, then X equal to.
He gave the matrix A, correct?
Yes, sir.
But one of the element he did not give us. He also provided eigenvector of A, correct?
Yes, sir.
We know that AX should be equal to what? Lambda X. We don't know lambda. We don't know one of the entry in A, correct?
Yes, sir.
See how we are going to do this. Again, this is also through verification only. What is A? Is it okay?
Yes, sir.
What is the vector they gave?
2 minus 2.
Should be equal to lambda times the same vector, na?
Yes, sir.
So you had a doubt, na? Like how do we multiply? This
Yes,
is
sir.
the row, this is the column. So multiply it. What do you get?
16, then minus plus 12, then 2.
Should be equal to what? 2 lambda.
Yes, sir.
So that means the value of lambda is 14, 13, 15.
Yes, sir.
Now, can you please read this into this?
Yes, sir. Minus 12 minus 2x minus 4
Equal to what?
minus 2 lambda.
Do you know the value of lambda?
15.
Yeah, substitute that. So this is like minus 2x equal to minus 30 plus 12. Can you help me with what's the value of x?
9.
Yes. Again, the basic idea is this. If you call lambda as eigenvalue, x as eigenvector, then ax should be equal to what? Lambda x.
Lambda x.
Okay. Okay. So if you have any other doubt, we will discuss that at the end. Okay.
Okay, sir.
So like closely you follow the lecture. Okay.
Yes, sir.
Hello.
Tanmay?
Excuse me, sir.
Yes.
Hello.
Sir,
Sir,
can you hear me?
Who is
This is Tanmay. Hello.
Tanmay, you can talk to me.
Yes, sir. Sir, in this minus 2x equal to minus 30 plus 12 and plus 4, sir.
Oh, did I do any? Which one? Which are you talking about?
In the while calculating x, you took only minus 12 to the right hand side. You should also take minus 4, no, sir.
See,
right side of the page.
Okay.
Calculation mistake.
Yeah, I got what you're saying. Thanks for that.
Thanks.
Wait. You wait.
Okay, sir.
So you help me with this calculation, yeah.
Okay, sir.
So this
Minus
is
30.
going to be plus 16, na?
Yes, sir.
So minus 2x would be minus 14, which means
Yes,
x is 7.
Yes, sir.
Maybe others are also like raised hand to tell this. Okay, nice. Yes. Tanmay, read this.
If the eigenvectors of the matrix 3, 4, 4 minus 3 are A1 and 1B, then A plus B equal to.
This was actually asked in your engineering services exam. This question appeared in engineering services. Can you tell me, Tanmay, what kind of matrix is given in the problem?
Symmetric matrix, sir.
So I'll just write that. Given I want to tell you a property of symmetric matrix. So look at this.
Okay, sir.
Do you know what I'm going to write?
No, sir.
Can you guess? Come on, yaar, guess it.
Are perpendicular, sir.
Yes. The eigenvectors of symmetric matrix are perpendicular to each other. That means if you treat this as E1, this as E2, what do we know is
E1 transpose
E2 will give you what?
0.
Yeah. How does E1 transpose look like? It looks like
A1.
So
and 1B.
This product must be what? 0.
0.
Do you know how to take the product?
Yes, sir.
This row into this column. Help me.
Yes, sir. A plus B equal to 0.
0. If you know this property, you would have saved a lot of time. It's like you need not find the eigenvalues. You need not find the eigenvectors. You need not compare it with A1, 1B. And then you need not take A plus B. Directly you got the value as what? A plus B equal to?
0.
0. That means in the exam, what is tested is properties of eigenvalues and eigenvectors. Okay. Is this related to symmetric matrix?
Yes, sir.
Will you apply only to symmetric matrix or any matrix?
Only for symmetric matrix. Sir.
Only for symmetric matrix. Okay. I would like to add one more property for symmetric matrix. Okay. So I want you to read it. Okay, Tanmay. Thanks for pointing out the mistake. Can you read this, Tanmay?
Yes. For a symmetric matrix, the number of non-zero eigenvalues of the matrix is equal to the rank of the matrix.
This is applicable only to what?
Symmetric matrix.
This talks about what? This property talks about the number of non-zero eigenvalues of the matrix. Okay?
Yes.
This particular property has been asked in the gate for 2 marks. Okay? More, I mean, in the recent gate, if you look at the papers, there are 2 mark questions on this particular property. So that's the reason I'm highlighting this property. Once again, this is
for a
applicable to
symmetric
which kind of matrix?
Symmetric matrix.
It talks about what kind of eigenvalues?
Non-zero eigenvalues.
How many non-zero eigenvalues will a symmetric matrix have?
Rank of the matrix.
Yes, rank of that matrix. Okay, nice. Extraordinary. Now, Tanmay, we'll see whether you will help me or not. Read the question. Give me your opinion.
The distinct eigenvalues of A
are. Can you also read the options?
0, n, 1, n minus 1, 0, n minus 1, 1, n.
Answer my questions. Is the given matrix symmetric or not?
Symmetric, sir.
Okay, symmetric. I'll write that. Can you tell me what is rank of A?
1, sir.
How did you tell?
We can
make the second row, third row, so on the last row, all
0.
zeros, correct?
Yes, sir.
Yes, very good. Nice. What is rank of A? Once again, please.
1.
My dear students, are you listening to Tanmay or not? Rank, he says 1. Is it a symmetric matrix, Tanmay?
Yes, sir.
Is the rank equal to 1?
Yes, sir.
How many non-zero eigenvalues are there?
1.
Only 1. Correct?
Yes, sir.
Tanmay, total eigenvalues are? N.
2.
N.
Yes, sir. N, sir.
N cross N matrix.
Yes, sir.
For 2 cross 2, it is 2. For 3 cross 3, it is 3. For N cross N?
N.
N. Total eigenvalues are N.
N.
But among them, there is only one eigenvalue, which is non-zero.
Non-zero.
How many are zeros?
N minus 1.
Correct. That means I'll just write let the eigen values be something like lambda 0, 0, so on 0. Is that okay?
Yes, sir.
Where I'll clearly mention that lambda is not equal to 0. Is that fine?
Yes, sir.
Can you tell me what is sum of these eigenvalues?
Lambda.
This should be equal to what? Trace.
Trace, n.
What is trace?
N, sir. I mean, 1 plus 1 plus 1 equal
Lambda
to
must be what?
n.
What are the eigenvalues now? One eigenvalue is n. The other eigenvalues are all
0.
0. Read the question.
Distinct eigenvalues.
What are the distinct eigenvalues?
0, n.
Which is that answer?
Option A.
Okay, this is method 1. Let's look at method 2, which is even more interesting, but little lengthy, but interesting. Are you ready for that, Tanmay?
Yes, sir.
To the complete class, you tell me the interesting properties that we have seen here. Can you tell me the properties?
In this question, in method 1.
What properties you have used? Can you just give a recap to the class?
So if the given matrix is symmetric, then number of non-zero eigenvalues equal to rank of the matrix, and sum of the eigenvalues is equal to trace of the matrix.
Nice. Okay. So I'll write here. Let's look at method 2, which is very, very interesting. Method 2. Can you give me what is A?
1, 1, 1, 1, 1, 10 times. N into
Can
n.
you help me? What is A minus lambda I?
Yes, sir. 1 minus lambda, 1, 1, 1, and so on. 1, 1 minus lambda, and so on, 1. Similarly, 1, and so on, 1 minus lambda.
Are you looking at the determinant of this?
Yes, sir.
I'm looking at the determinant of this, correct?
Yes, sir.
Will you equate that to 0?
Yes, sir.
Because the characteristic equation, when you equate that to 0, that is when you get the eigenvalues.
Eigenvalues, we can get the lambda values.
Tanmay, is this a matrix?
Yes, sir.
Is this a determinant?
Yes, sir.
Okay, listen. Did you attend yesterday and day before the class?
Yes, sir.
Can you tell me what would be this when you replace R1 with R1 plus R2 plus so on plus Rn? Can you give me the elements of the first row?
N minus lambda, n, and so on. Yes, sir. N minus lambda, n. Yes, sir.
All the elements are n minus lambda.
N minus lambda. Yes, sir.
Second row.
1, 1 minus lambda, and so on, 1. 1, and so on, 1 minus lambda. Yes, sir.
What is common in the first row?
N minus lambda.
I put out because the properties of the determinants will allow to do that. Okay.
Yes, sir.
Look at one more step. Something like this. R2 is R2 minus R1. R3 is R3 minus R1. So on. Rn is Rn minus R1. Will the determinant change?
No, sir.
Because it's a type 3 operation.
Type 3 operator.
Okay. So now this is n minus lambda out. The first row is all ones.
All ones.
Help me with the second row.
Yes, sir. R2 equal to R2. Yes, sir. 0. 1 minute, sir. Minus lambda.
Very good.
All zeros.
Very good. Last row, please.
0. Last one is minus.
Third row
0.
Something like 0.
0, 0, minus lambda. All zeros.
Last row.
All zeros except last one is minus lambda.
Is this equal to 0? Yes.
Yes, sir.
This is looking like a triangular matrix.
Yes, sir.
The determinant of this triangular matrix is simply the product of the principal diagonal.
Principal diagonals.
So this is something like n minus lambda into minus 1 whole power n minus 1 into lambda power n minus 1, because this is
Yes,
1.
sir.
The remaining are lambdas, no? So this is 0.
Yes, sir.
From this, it's very clear that lambda is n, comma 0, comma so on 0.
Yes.
Okay, this is also very, very useful procedure. It is lengthy, but very, very useful in the exam. I hope
Yes,
you
sir.
got this idea.
So I got this idea, but for this question, method 1 is it will take less time, no, sir. When we take
But all the problems cannot be solved like this.
Okay. Yes, sir.
Is that okay?
Yes, sir.
Nice. So we will go ahead. We'll go ahead. Now, maybe let me talk to some other student.
Okay, sir. Thank you, sir.
Trivikram. Let's talk to Trivikram.
Yes, sir.
Usha, Maunika also be ready. Yeah. Can you read this question, Trivikram? Can you give me your ideas?
The product of the non-zero eigenvalues of the matrix. Should I read the matrix?
See here. I'll give you 1 minute time, Trivikram. Okay. See what you can do it. Okay. Don't worry if your answer is wrong also. Okay. Just go through that. Tell me what ideas you get.
Symmetric matrix.
Oh, you are saying it's a symmetric matrix? I agree to that. Good. Next.
If you change it to row echelon, we can find rank.
Okay, nice. Nice. You are moving in a perfect direction.
After that, we can find the number of non-zero
Super.
eigenvalues.
Nice. Nice. But he's not asking about the number of non-zero eigenvalues. He's asking product of non-zero eigenvalues. That means you need those non-zero eigenvalues. Okay. Most of the students, Trivikram, what happens? They'll see the question this way, product of eigenvalues. They feel product of eigenvalues means it's a determinant, na?
Yes, sir.
Product of eigenvalues is a determinant or not?
Yes, sir.
Determinant of which matrix? Determinant of the given matrix.
Sir.
What is the first row? 1 0 0 0
1
1.
0
What is the
0
last
0
row?
1. 1 0 0 0 1. Determinant.
Are they identical?
Yes, sir.
If they are identical, the determinant is 0, na?
Yes.
The determinant is 0 means product of all the eigenvalues is 0. Product of all the eigenvalues is 0. But are they asking product of all the eigenvalues?
No, sir. Non-zero eigenvalues.
Only non-zero eigenvalues. So because of that, what we have to do is we have to do what you said. First is find the rank. Okay. R1, let's say R5. R5 is R5 minus R1. Okay. R3 is R3 minus R2. R4 is R4 minus R2. Can you give me what would be the matrix?
1 0 0 0 1 0 1 1 1 0 and all zeros, sir.
Very good. What is the rank?
2.
Rank.
2, sir. 2.
How many non-zero eigenvalues are there?
2.
So I'll also highlight the symmetric matrix. So there are only 2 non-zero eigenvalues. Is that okay?
Yes, sir.
If 2 are non-zero, how many are 0?
5 minus 2, 3.
Yes. I don't care about those 3 zero eigenvalues. I just want the 2 non-zero eigenvalues. Is that okay?
Yes, sir.
Can you tell me what is A minus lambda I?
1 minus lambda 0 0 0 1 0, 1 minus lambda, 1, 1, 0, 0, 1, 1 minus lambda, 1, 0, 0, 1, 1, 1 minus lambda, 0, 1, 0, 0, 0, 1 minus lambda.
Okay, nice. So far, it is very good. I should equate this to 0, na?
Yes, sir.
Because the characteristic equation is you have to equate the characteristic equation to, characteristic equation means determinant of a minus lambda equal to 0. Okay, look at the step. R1 is R1 plus R5. R2 is R2 plus R3 plus R4. Will this kind of operations change the determinant?
Yes.
Can you tell me what is R1 now?
2 minus lambda, 0, 0, 0, 2 minus lambda.
Very good. What is
R2? 0, 3 minus lambda, 3 minus lambda, 3 minus lambda, 0.
Okay, see, your friend is saying R1 is simply now 2 minus lambda, 0, 0, 0, 2 minus lambda, it seems. R3 is 0, R2 is 0, 3 minus lambda, 3 minus lambda, 3 minus lambda, 0, it seems. I'll write that. So with this, what I get is 2 minus lambda, 0, 0, 0, 2 minus lambda. What is common in the first row?
2 minus lambda.
What is common in the second row?
3 minus lambda.
I don't care about the entries in the determinant. Okay.
Two values.
From this, lambda is 2 and 3. Obviously, what could be the other eigenvalues?
Zeros.
It will be 0, 0, 0, correct?
Yes.
What is product of non-zero eigenvalues?
6.
This is a 2-mark question in your GATE exam. Product of non-zero eigenvalues. Okay, so a question can be framed this way. Nice. Okay, one more question you help me here. Yeah, this appeared in 2017 GATE exam. Can you help me?
Yes. Should I read the question?
Hmm.
Consider the 5 into 5 matrix. It is given that A has only one real eigenvalue. Then the real eigenvalue of A is.
Okay, my question is it symmetric?
No, sir.
Is it symmetric?
No, sir.
So you can't apply the properties of symmetric matrix, na?
Yes.
Okay, okay. But if you see, it looks like the pattern. There is some pattern in the matrix, correct?
Yes, sir.
Acha, you are, I forgot your name. Trivikram.
Yes, sir.
Trivikram, tell me what happens if I do an operation like R1 replaced with R1 plus R2 plus R3 plus R4 plus R5.
Sum will be same.
Huh?
1 plus 5 plus 4 plus 3 plus 2. Sum is same for all.
That means the first row, will it be same?
Yes, sir.
What would be the entries of the first row?
15.
Okay. Okay. How many eigen values this matrix is going to have?
1.
It is going to have 5 eigen values.
5. Yes.
What is given in the problem? It is given that it is given that one real eigenvalue is there and the remaining 4 are actually, it may be complex. Imagine your complex. Only one real eigenvalue we have and is asking the value of that real eigenvalue. Okay. So Trivikram, are you there?
Yes, sir. Yes, sir.
Yeah. So can you tell me what is A minus lambda I?
1 minus lambda 2, 3, 4, 5. 5, 1 minus lambda 2, 3, 4.
Continue.
4, 5, 1 minus lambda 2, 3. 3, 4, 5, 1 minus lambda 2. 2, 3, 4, 5, 1 minus lambda.
The determinant should be equal to what?
I equals to 0. Yes.
Now R1
R1
replaced with
R1 plus R2 plus R3 plus R4 plus R4.
what are the entries in the first row?
15 minus lambda.
Are all 15 minus lambda?
Yes, sir.
I don't care about the other values. Okay, some values.
Yeah.
This must be equal to 0, na?
Yes, sir.
What is common in the first row?
15 minus lambda.
It is left over. Now this must be equal to what?
0.
0. It's very clear that lambda is 15. Now can I directly answer that the answer is 15?
Yes, sir.
What about the other eigenvalues?
They are all complex.
So I don't care about them. There is only one real eigenvalue and is asking that. Okay.
Yes.
Listen, my dear students, if you don't know these properties in the examination hall, if you try to expand a 5 cross 5 determinant, all the 3 R's will be utilized only to solve this 5 cross 5 determinant. Okay, so you will be very much frustrated after solving this. What is the crucial thing is, you need to know properties of eigenvalues and eigenvectors. You need to know the properties of determinants, which operations won't change the determinants. So that's a crucial thing here. Okay. Yeah, so this is how a problem can be framed in the exam. Okay, so let's talk to a few more students. Karunya.
Hello.
So new students, I'll interact with new students. Whoever is going to raise the hand, I'll talk to them. We'll ask their opinion, how to proceed. Yeah, Karunya, are you there?
Yes, sir.
Yeah, go ahead. Give me some suggestions regarding this question.
Consider the matrix A whose eigenvalues are 1, -1, and 3 in the trace of A power 4 minus 3A cube.
Okay, this appeared in 2016 gate. Now, can you tell me what could be the eigenvalues of A power 4?
It's lambda power 4, sir. 1
What
power
could
4
be the-
-1.
Yes, continue.
1 power 4 -1 whole power 4 and 3 power 4.
What are the eigenvalues of A power 3?
It's 1 cube -1 whole cube and 3 cube.
Now, can you tell me what are eigenvalues of A power 4 minus 3A cube?
Yes, sir. It's 1.
Something like 1 power 4.
1, 1, 27.
No, we will do it in a step by step, okay? This is one eigenvalue. What could be the second eigenvalue?
-1 whole power 4 minus 3 times of -1 whole cube.
The last eigenvalue?
3 power 4 minus 3 minus 3 power cube.
So finally, tell me what are the eigenvalues?
-2, 4. What is the
0. Correct?
Sir, no, sir.
Actually, this is 3 power 4. I wrote it wrong. Check it.
I see.
Yeah, now this is fine. Huh?
Yes.
Can you also tell me this? What would be trace of E matrix?
Some of the eigenvalues. It's going to be 2.
That means trace of a power 4 minus 3a power 3 is simply minus 2 plus 4 plus 0, which is how much? So a question can be asked like this, which is based on what again? Properties of eigenvalues and eigenvectors.
So a small doubt on the previous question, sir. Product of non-zero eigenvalues of a matrix.
Okay, what is
Sir,
your doubt?
actually, after reducing this into row echelon form, so I actually thought that the non-zero eigenvalues are 1, 1, and I thought the product was 1, but you made that into a minus lambda and applied the operation. So why can't we take it as 1? Actually, we got the in row echelon form, and also it's in the triangular form. So diagonal elements are nothing but the eigenvalues.
Wait. You are going wrong. Actually, you are thinking in the wrong way. I have to find the determinant of a minus lambda I. Okay. For that, I have used these operations. These operations will not change the determinant. I got new entries. Yes. The first row I have taken common, that is 2 minus lambda. Second row also there is something common, that is 3 minus lambda. Now after taking that, I get entries like this. And so on. Right, you have to find the determinant of this. Is that okay?
Okay.
This is not in the row echelon form. You need to use this element, make this 0. Use this, make this 0. When you do that, the other eigenvalues would be all zeros.
Yes.
Okay, so you need to do that analysis. Hello?
Yes, sir, I understood, sir.
Here, in this step itself, I got lambda as 2, 3. That means by default, the other eigenvalues must be 0, because for a symmetric matrix, the number of non-zero eigenvalues is equal to rank.
Yes, sir.
Is that okay?
Yes, sir. Got
it. Please, you do this activity. Fill all these elements properly. Try to find the determinant. The determinant will turn out to be lambda cube here. When you equate the lambda cube to 0, you get lambda as 0, 0, 0.
Okay.
Okay. Let's talk to another student here. Let's try to see their opinions about the questions. Uday Sri.
Yes, sir.
Yeah, Uday Sri, we are done with the problems. We have some concepts now. Few more concepts. So I need some assistance from you. Will you help me?
Yes,
so the concept is Cayley-Hamilton theorem, which is also a very, very simple observation. Let's see what is this saying. Every square matrix satisfies its own characteristic equation, it seems. Let's see what does this mean. I've taken a matrix called A. How do you get the characteristic equation? Do you get it like this? Can you tell me what is the characteristic equation here? If you simplify, what do you get?
Lambda square minus 5 lambda plus 4.
Right. So we call this as characteristic equation. Characteristic equation in what? Lambda. Characteristic equation in lambda is given by what? Lambda square minus 5 lambda plus 4 equal to 0. Now try to read this. Can you please read it?
Characteristic equation in A.
Yeah, what could, nice. What could be the characteristic equation in A?
A square minus 5A plus 4 equals to 0.
Plus?
4i.
Yeah, it should be 4i, right? Otherwise it is meaningless. equal to what?
0.
0 means what?
Null matrix.
Null matrix. Now read this statement.
Every square matrix satisfies its own characteristic equation.
That means what? You are given a matrix, get the characteristic equation. In that characteristic equation, instead of lambda, if you put A, that will also satisfy itself. So how do you confirm that? Is I'll do one verification here. So look at that verification. I got characteristic equation in A, which is a square minus 5a plus 4i equal to 0. I need to verify. Can you give me the entries of a square?
11, 10, 5, 6.
Nice. So can you tell me what would be this a square minus 5a plus 4i? A square is 11, 10, 5, 6. Minus what would be 5a?
5, 10.
4i means?
4, 0, 0, 4.
Let's see whether this will give me 0 or not. 11 minus 15 plus 4 is how much?
0.
10 minus 10 plus 0. 5 minus 5 plus 0. 6 minus 10 plus 4, how much?
0.
Like, is your characteristic equation verified?
Yes.
Now you may get a doubt. Student may get a doubt, sir, is it true for only this matrix or any square matrix? This is true for any square matrix. Is that clear?
Yes,
So one consequence of this is you can actually find higher powers of A and A inverse using the characteristic equation. Can you repeat what I said?
You can find higher powers of A and A inverse using this characteristic equation.
How do you find that? I will show you now. Using the Cayley-Hamilton theorem or using the characteristic equation, we can find higher powers of A and A inverse in an effective way. So let's see how is that possible. How is this possible? So Cayley-Hamilton theorem is used to find higher powers of A and inverse of A. How is that possible? Let's verify. What is the characteristic polynomial in A? In the earlier example?
Minus 4, 5a plus 4i equals to 0.
What could be A square?
11, 5 minus 4.
Okay, let's multiply A on both sides. So this, when I multiply A on both sides, this becomes A cube, which is 5a square minus 4a. What I would like to do is, I would like to substitute in the place of A square this expression. Let's see, what do we get? We get A cube as 25a minus 20i minus 4a. So this is going to give me 21a minus 20i. Finding A cube is now so simple. It is simply 21a minus 20i. What could be A power 4? For A power 4, what I'll do is I'll write like this, A cube into A. Let's multiply it. I get 21a square minus 20a. What is the substitution in the place of A square? 5a minus 4i minus 20a. Can you give me the simplified form? 21 5s are 105. 105 minus 20 is 85, I guess. 85a minus 84i. Finding a power 4 is now so simple. It is simply 85a minus 84i. So using this characteristic equation in A, you can actually find higher powers of A easily. That is one advantage. Okay, so let me also show you how to find A inverse. Let's find A inverse. So for that, what I'll do is I'll again go back to the characteristic equation. This time I'll write what is 4i. Can you help me? What is 4i?
I minus a square.
What is I?
4y minus a square by 4.
I need A inverse, so I'll multiply A inverse on both sides. A inverse would be 5i minus A by 4. Is that clear? So what we have done, multiplied A inverse on both sides. Okay, I hope you understood this. Okay, so we will talk to different students here. Let's see a maximum number of students. Let's talk. So this is about Cayley-Hamilton theorem. I'll quickly summarize what is Cayley-Hamilton theorem. It says that every square matrix satisfies its own characteristic equation. So for that, what you need to do is to verify. For that, what you need to do is get the characteristic equation in lambda and then find characteristic equation in A. My suggestion would be, whenever you see a polynomial of A in the question, whenever you see a polynomial of A in the question, you need to use Cayley-Hamilton theorem. So that will definitely help you. So let me present one problem in front of you. I'll give you some time. Pavitra? Your mic is not working, Pavitra. Hello? Dear students, go through this 28 problem. Let me know your idea.
Hello, sir.
See, Pavitra, your network connectivity is not good. Can you hear me? Okay, I'm muting you.
Yes, sir.
Dear students, go through this problem. The hint that I'm going to provide you is, whenever you see a polynomial of A in the question, first get characteristic equation in lambda, get characteristic equation in A, use that characteristic equation in A to solve the problem. Yeah, please go through this. If anyone has any idea, please let me know. I'll give you a few minutes time, 2-3 minutes time. Get me the answer. I'm waiting for your approach.
Sir, this is Tanmay.
Yes, Tanmay.
So first we have to find characteristic equation. Now the characteristic equation is lambda cube.
Okay, wait, I'll write it nice. So Tanmay says the character. Okay, tell me what is A minus lambda?
A minus lambda is 1 minus lambda, 0, minus 1, minus 1, 2 minus lambda, 0, 0, 0, 2 minus lambda.
Minus 2 minus lambda, I guess.
Yes, sir. Minus 2 minus lambda.
Okay. You expanded this?
Yes, sir. Can I say
How much
direct?
you got? You can tell me.
Lambda cube minus lambda square minus 4 lambda.
Okay.
Plus 4.
Huh?
Plus 4.
So this is the characteristic equation in lambda?
Yes, sir.
Can you tell me characteristic equation in A?
A cube.
Okay.
Minus a square. Minus 4a 4a plus 4i.
Will this always be a null matrix?
Yes, sir.
Can you guide me? What should I do next?
Next, add 2a on both sides, sir. 2i.
Add 2i on both sides. Okay, nice. Yes, I understood what you're saying. You are now looking at B, na? That
yes,
is
sir.
A cube minus a square minus 4a plus 6i. Can I split that 6i?
Yes, sir.
Plus 4i plus 2i. Can you help me? How much is this?
0, null matrix.
So null matrix plus 2i. How much is B finally?
2, 0 or 2i.
Give me the entries. 2,
2, 0, 0, 2. Oh, sorry. 0, 2, 0, 0, 0, 2.
Yeah, please answer the question.
Retirement of base word.
How much?
8.
Very good. Nice. I hope others are also getting the same answer. If you have got the same answer, type it in the question and answer box. Saket says minus 8. Saket, please correct it. Niraj, Kiran Kumar. Yeah, you're all right. Akshaya, sorry, Akshaya, I could not take your doubt. Right? You said it 8, correct? But at the end, at least you be in touch. I'll clarify your doubt. Okay, Akshaya. From tomorrow onwards, next class onwards, make sure your mic is working. I would have interacted with you, yeah. Okay, most of the students have typed the answer as 8. Good. We are almost like about to finish this course. There are few more small topics left over. Let me complete that and then we'll have a doubt session. A very, very important topic we are going to discuss now. Simple and important. So who will interact? Rakshit, are you there?
Yes, sir.
Rakshit, so far, I hope you are like following this lecture.
Yes, sir.
Okay. Rakshit, we have got few more things to discuss. Yeah. One is algebraic multiplicity, geometric multiplicity. Is that okay?
Yes, sir.
What are the next 2 topics? Algebraic multiplicity and
Geometric multiplicity.
These are very simple concepts, especially the geometric multiplicity you already know. Okay, I just have to put some light on it. You already, through some examples, you have learned what is geometric multiplicity. Okay, so can you help me with this algebraic multiplicity? Can you just go through that?
Algebraic multiplicity of an eigenvalue. If an eigenvalue lambda of a square matrix A of order n is repeated m times, then the number m is called the algebraic multiplicity of the eigenvalue lambda.
He's saying that A is a matrix whose order is n. So it will have n eigenvalues. Among them, there is one eigenvalue it seems, which is repeating how many times?
M times.
Then m is called the algebraic multiplicity of that eigenvalue lambda. Is it simple or not? The number of times an eigenvalue is repeating is nothing but your algebraic multiplicity. Okay?
Yes, sir.
Shall we check this?
Yes, sir.
Okay. Look at this example. Example 1. Can you tell me what kind of matrix is A?
upper triangular matrix.
Upper triangular. What could be the eigenvalues?
2, 0, 1, sir.
Because for a triangular or for a diagonal, the eigenvalues are simply
the principal diagonal elements.
Very good. How many times is the eigenvalue 2 repeating?
It is not repeating.
It is repeating only once, na? I mean,
Yes.
it is occurring only once.
Occurring once.
So algebraic multiplicity of lambda equal to 2 is simply 1.
1.
Algebraic multiplicity of lambda equal to 0 is also 1. Algebraic multiplicity of lambda equal to 1, is it also 1?
1.
Now help me with example 2. Eigenvalues, please.
2, 2, and 3.
How did you tell that quickly?
It's a triangular matrix again.
So you tell to the class that it's a upper triangular matrix. If you are dealing with upper triangular or a lower triangular or a diagonal, the principal diagonal elements are the
Eigenvalues of the matrix.
Will you apply this to every problem? No,
in the sense,
only to upper triangular, lower triangular,
lower
or
triangular and
diagonal
diagonal
matrices.
matrix.
What is the algebraic multiplicity of lambda equal to 2?
2, sir.
Because it is occurring
2 times.
2 times. What is the algebraic multiplicity of lambda equal to 3?
1.
Very, very simple observations. Give me the eigenvalues of example 3.
Again, it is an upper triangular matrix. So 1, 1, 1 will be the eigenvalues of the example.
Okay. Next one. What is the algebraic multiplicity of lambda equal to 1?
3.
This is very, very simple discussion. Okay. Are you following this, Rakshit?
Yes, sir.
Now, Bumrah's Yorker is going to come at you. Are you ready?
Yes, sir.
Yeah. What is the heading?
Geometric multiplicity of an eigenvalue.
Okay. Geometric multiplicity means the number of linearly independent eigenvectors associated with a particular eigenvalue. Okay. So to make the things very simple, Rakshit, for a system like this, how many linearly independent solutions are there? You are following homogeneous from the first class, na?
Yes, sir. Following from the first class.
For Bx equal to 0, how many linearly independent solutions are there? For Bx equal to 0, how many linearly independent solutions are there? The answer is n minus r.
Yes, sir.
You forgot it?
No, sir.
Okay, so I'll write for Bx equal to 0, we have n minus r linearly
independent.
Now listen to me carefully. We have a new system here, a minus lambda I times x equal to 0. Is it also homogeneous?
Yes, sir.
Okay, for a minus lambda I times x equal to 0, we have n minus r linearly independent. Instead of solutions, I call eigenvectors because x here is called as eigenvector, na?
Yes, sir.
Eigenvectors. Acha, Rakshit, can you tell me what is r in this discussion here?
Sir, rank of B.
B. What is r here?
Rank of a minus lambda I.
Yes, that is very, very important because earlier it was about Bx equal to 0. In the present problem, it is a minus lambda I times x. Is that okay?
Yes, sir.
Again and again, I'll repeat. How many linearly independent eigenvectors are there for a particular eigenvalue called lambda. What is the answer?
For lambda.
For a particular eigenvalue lambda, how many linearly independent eigenvectors are there? The answer is
n minus r.
minus r. What is r?
R is rank of A minus lambda. Sir.
Don't ever get confused. Here, it's about a system called A minus lambda I times of x equal to 0. So here rank is calculated on A minus lambda I, not on A.
Yes, sir.
Is that clear? Yeah. Can
Yes,
you please read that heading and continue that?
Hello.
Can you please read it?
Geometric multiplicity of an eigenvalue. If the number P is the number of linearly independent eigenvectors of matrix A of order n corresponding to an eigenvalue lambda, then P is called the geometric multiplicity of lambda, and it is given by P equal to n minus r. That is the number of variables minus
that
rho into
that
A minus
notation.
lambda.
That notation rho is called rank. Okay, rank of.
Okay, rank of A minus lambda.
You need to read this as what? Rank. Of. Okay, so n minus r. Is that okay?
Yes, sir.
Okay, I'll give you a note point, my dear students. Look at this note point here. Yeah, can you help me read this, Rakshit?
If a matrix A of the order n cross n has n distinct eigenvalues, then there are n linearly independent eigenvectors.
The nice thing is you need not check whether they are linearly independent. I mean, if you find the eigenvalues to be distinct, all are distinct, then you'll have n linearly independent eigenvectors. They'll ask this kind of questions in the exam. Okay, this is a very, very important point. Next point you see. Can you read this?
If a matrix A of the order n cross n has some of the eigenvalues repeated, then the matrix A may or may not have n linearly independent eigenvectors.
These are very, very important statements. What I'll do is I'll take you to one example. Okay, this example. What are the eigenvalues here?
So 1 and 4.
Are they distinct?
Yes, sir.
What is the order of A?
Order of
A.
2 cross 2, sir.
Order of A is 2 cross 2. It has got two distinct eigenvalues. This will give you two linearly independent eigenvectors. Are you ready to see them?
Yes, sir.
Did we get the eigenvectors?
Yes, sir.
The first one belongs to lambda equal to 1, correct?
Yes, sir.
The second one belongs to lambda equal to 4. Are they linearly independent or not?
Yes, sir.
So what points did I tell you now? Yeah, can you please again read this for me?
If a matrix A has n distinct eigenvalues, then there are n linearly independent eigenvectors.
So you need not check it. It's very, very easy. Okay.
Yes, sir.
If the eigenvalues are all distinct, there are odd. My Bluetooth.
Can't hear, sir.
Rakshit, can you hear me?
Yeah, sir. Now I can hear you.
Yeah, yeah. So suddenly my Bluetooth switched off. Give me some time. I'll be back with the Bluetooth charging. Till then, I'll just use my laptop mic. Yeah. Can you please read those two statements?
If a matrix A of the order n cross n has n distinct eigenvalues, then there are n linearly independent eigenvectors.
Yes. If some of the eigenvalues are repeated?
If a matrix A n cross n has some of the eigenvalues repeated, then the matrix A may or may not have n linearly independent eigenvectors.
Okay. Now, I'll talk to another student here. Let me talk to Ashish.
Yes, sir.
We are almost about to close the session, okay? So give me some time, we will do it in a nice way. Ashish, are you there?
Yes, sir.
The concept of geometric multiplicity is like somewhat difficult, yeah. Okay, so I'll
Okay, sir.
definitely put my 100% effort to make sure you'll understand it. Can you read this question?
The number of linearly independent eigenvectors of the matrix A is 820 minus 4008 001.
Can you tell me what are the eigenvalues?
2 and 1. Because triangular matrix 2 and 1.
Yeah.
Oh,
What are
0,
the
0
eigenvalues?
also 201.
Do you have 3 distinct eigenvalues?
Yes, sir.
Three distinct eigenvalues. So there are 3 distinct eigenvalues. So this is going to lead to what?
Property 1 you mentioned earlier. Forgot.
It gives 3 linearly.
Oh yeah, 3 linearly independent eigenvectors.
So what's the answer for this question?
Oh, number of, that's 3.
Yes. So the answer for this question is 3.
Yes, sir.
I want you to be very, very attentive in the next problem. Okay. Next problem is very, very important. This appeared in the GATE exam.
Okay, sir.
Are you ready?
Yes, sir.
The other students see whether we are doing it correctly or not. Yeah. Please go ahead with the question.
The number of linearly independent eigenvectors of the matrix A 201, 021, 003.
Can you provide me the eigenvalues of this matrix?
Eigenvalues are 2, 2, 3. There is repetition.
Now, when eigenvalues are repeated, the matrix may or may not have
linear independent.
n linearly independent eigenvectors. In this question, 3. Correct?
Yes, sir. May
Let's
or may
find
not have 3.
For lambda equal to 2. Can you give me what is a minus lambda I?
Okay, sir. For which okay, lambda equal to 2.
Firstly, like give me what is a minus lambda I matrix.
2 minus lambda 0 1 0 2 minus lambda 1 0 0 3 minus lambda. Then
Now put lambda equal to 2.
0 0 1.
I'll just clear this.
Oh, okay, sir.
I'll say for lambda equal to 2, give me what is a minus lambda I?
0 0 1 0 0 1 0 0 1.
You know why am I finding this? I need rank of a minus lambda I.
That's 1.
For that, what you will do is
R2 minus R3.
Anyway, you said it has 1. You are right actually.
Yes, sir.
So what you get is 0 0 1 0 0 0 0 0. Can you tell me what is rank?
Rank is 1, sir.
But what I need is something like this. Corresponding to lambda equal to 2 is given by n minus rank of a minus 2i. Am I right?
Yes, sir.
What is n?
Number of 3.
What is rank?
Rank is 1, sir.
That means what?
2.
The number of linearly independent eigenvectors for lambda equal to 2 is 2.
2.
Keep this aside. Keep this aside. For lambda equal to what?
Sir, I didn't understand what exactly happened in the last step.
What happened is we took lambda equal to 2.
Yes, sir.
Calculated its rank.
Okay.
Okay, calculated a minus lambda is rank. For that we got 1.
Okay, sir.
So now number of linearly independent solutions is given by n minus r.
Okay. Okay, sir.
I calculated n minus r, which turned out to be 2.
Okay, back from the first day. N minus r. Understood,
Okay,
sir.
we are like dealing with that from day 1.
Okay, sir. Now I remember.
What is a minus lambda I for lambda equal to 3?
Minus 1 0 1 0 minus 1 0 1. Can you show me that? Okay, 0 minus 1 1 0 0 0.
What is the rank?
Rank is it's 2, I think.
Yes. Can you tell me how many are linearly independent eigenvectors corresponding to lambda equal to 3?
Okay, so 3 minus 2, that is 1.
Okay.
N minus r.
3 minus 2, which is 1.
1.
Okay.
Yes, sir.
Now comes the final thing. For lambda equal to 2, how many linearly independent eigenvectors you got?
Linearly independent, I got 2, sir.
For lambda equal to 3, how many linearly independent eigenvectors you got?
1, sir.
Now the conclusion. For the matrix A is, you need to add both the numbers that you have got.
2 plus 1.
Yes. How much?
3.
I have justified here. See here, when some of the eigenvalues are repeated, I clearly said the matrix A may or may not have
N.
Right. So in this case, it actually, even though the eigenvalues are repeating, the matrix is having 3 linearly independent eigenvectors. Is that okay?
Yes, sir. That may or may not happen.
Help here from you.
Okay, sir.
Right. Manager is calling me. Just a moment. Manager is calling me. Just a second.
I can wait, sir.
Hello. Hello.
Yes, sir.
Actually, manager has called regarding the schedule for mechanical people. Theory of machines, it seems. For civil ECE instrumentation, it's probability.
Same timing, sir.
Is that okay? Yeah, same timings only. I will also inquire that regarding the timings. Mostly same timings. I'll just ask him. I'll inform you as soon as he replies. Okay. So let's continue this discussion. Yeah. So I was about to write one comment here. What was that is? The number of linearly independent eigenvectors for the matrix A is what? 2 plus 1, which is 3. Is that okay?
Yes, sir.
One more small activity. Yeah. You read this question.
A number of linearly independent eigenvectors of the matrix A 1 1 0 0 1 0 0 0 1.
Can you give me the eigenvalues?
1 1 and 1.
Okay. We need to write A minus lambda I. Can you give me A minus lambda I entry?
1 minus lambda 1 0 0 1 minus lambda 0 0 0 1 minus lambda.
Now see the killer point. For lambda equal to 1, can you tell me what is A minus lambda I?
0 1 0 0 0 0 0 0 0.
Can you tell me what is rank?
1. Or 1, sir.
1. 1. Can you tell me how many linearly independent eigenvectors are there?
3 minus 1, most probably.
The number of linearly independent eigenvectors corresponding to lambda equal to 1 is how much?
3 minus 1.
Which is?
2.
2. Do you have any other distinct eigenvalue with you? Do you have any other distinct eigenvalue with you apart from?
No. 1 is the only value.
That means the number of linearly independent eigenvectors for the matrix is also
2.
2. We are done with the problem actually. Okay.
Yeah.
Is this matrix having 3 linearly independent eigenvectors?
No, sir. It's only 2.
Yes, only 2. Okay. So we will also write that comment. The number of linearly independent eigenvectors of the matrix A, how much?
2.
2. Is this matrix having complete set of linearly independent eigenvectors? No. Complete set means if it's a 3 cross 3, it should have 3 linearly independent eigenvectors. Is that having?
No, sir.
No. Okay. So keep that in mind. So most of our syllabus is done. I'll give you this problem as homework. Right? The notes will be uploaded. I have few more points to highlight. Okay. I'll just discuss those points and I'll leave you people. Okay. Can you, I'll talk to another student here. I'll talk to Utkarsh. I mean, it has been a long time I spoke to that guy. Utkarsh, are you there?
Yes, sir.
Utkarsh, are you following?
Yes, sir.
Utkarsh, we have one small discussion here. Very
Sure.
small discussion. Now you see that some matrices are having complete set of linearly independent eigenvectors.
Yeah.
Some matrices are not having complete set of linearly independent eigenvectors.
Right.
Matrices which do not have complete set of linearly independent eigenvectors are called deficient matrix or defective matrix. Is that clear?
Yeah.
Whenever a matrix possesses n linearly independent vectors, n linearly independent eigenvectors, such matrix can be diagonalizable. Okay. They'll ask you a question, my dears. What they'll ask is, when is a matrix diagonalizable? The answer is, whenever a matrix possesses n linearly independent eigenvectors. In such case, it would be diagonalizable. Okay.
Yeah.
I would like to tell you what is the meaning of diagonalizability. Okay, listen to this carefully. Very, very interesting. Small topic, but very, very interesting. Whenever A has n linearly independent eigenvectors, in such case, you can write A as A, D, P inverse. Okay? You can decompose A as what? P, D, P inverse.
P inverse.
Where D is diagonal.
Diagonal, yeah.
How does that look? It looks like this. Lambda 1.
0, 0. The diagonal elements are the eigenvalues.
Yes, the diagonal values are the eigenvalues. So where lambda 1, lambda 2, so on, lambda n are eigenvalues of what?
A. Original matrix A.
Okay, I'll talk about what is P inverse. Okay, after some time.
Yeah.
Okay, now if you are able to write A has P, D, P inverse, can you tell me what could be A square?
A into A, yeah.
Which is P,
D, P inverse
into
P, D, P.
Okay, what is P inverse into P?
I.
So this is going to give you P,
D square, yeah.
P inverse. Can you guess what would be A cube?
D cube, P, D cube, P inverse.
What would be A power 100?
Same, P, D power 100, P inverse.
What could be A power n?
P, D power n, P inverse.
See how easy is now finding higher powers of A.
Yeah.
If you have to find A power 100, usually what's the procedure is find A square, A cube, A power 10, A power 20, A 30, 90, 99.
99. Yeah.
A 99 into A.
Right, sir.
You know what is this telling? Don't do all such things. Find D power 100. You know what is D power 100? D power 100 is simply lambda power
100.
Lambda 2 power 100.
Yeah.
Lambda n per 100. This is very, very simple. And then multiply it with P,
and P
this
inverse.
side and P inverse from this side. Okay. With that, you get A per 100 easily. Correct?
Yes, sir.
But when is this possible? When A has n linearly independent eigenvectors. Okay. In the exam, this question got repeated. So A is diagonalizable when it possesses n linearly independent
linearly eigenvectors. Linearly independent eigenvectors.
Now you might ask, sir, what is P?
And P, yeah.
Yeah, I'll help you. What is P? I'll write it here. If A has n linearly independent eigenvectors, then P is simply E1, E2, so on, En put together.
Okay.
So I'll write where. What are E1, E2, so on, En?
The eigenvectors.
Eigenvectors of what?
Matrix A. And linearly independent, yeah. And linearly independent eigenvectors.
Vectors of what?
A.
Do you know how to construct P?
Yes, sir.
You know how to get P inverse?
Yes.
Yes. With this logic, you can find higher powers of A.
A.
Right?
Yeah.
So this is one application of diagonalizability. Is that clear?
Yes, sir.
Okay. Now, my dear students, listen to me carefully. Let me first give you the tomorrow's class. For mechanical students, theory of machines. For civil, ECE and instrumentation, it's probability class. Okay, that is the schedule. And the timings are 5 p.m. to 9 p.m. I have messaged him. So he's saying 5 p.m. to 9 p.m. I hope the message is very clear. Okay. Now, I have one more small topic, which is only for ECE students. Okay. Which is only for ECE students. It may take 15 to 20 minutes. I know most of the students will be having doubts. What I'll do is first I'll complete that topic and then take students' doubts. The other branch students, you can go for a break, come back within 20 minutes. Only ECE students stay back. I'm going to explain you what is a vector space. After the 20 minutes, if you have any doubts, you can ask me. Is that clear to everyone?
Yes, sir.
Yeah. Only for ECE. I'll first write that. I'll give you 2-3 minutes. Other students, just you can go take some break and come back. ECE people, just be here. ECE people, raise your hands here so that I can identify you easily. After 20 or 25 minutes, I'll conduct the doubts. Okay, you can ask me. Let me talk to Hussein. Hussein, are you there?
Yes, sir.
I hope you are following this lecture, Hussein.
Yes, sir. Yes, sir.
Okay. Vector space here. We need to talk about vector space. What you people should learn is, first thing you should know what is a vector space. What is a subspace? What is a dimension? What is basis? Can you just tell me the names that I said?
Vector space, dimension, basis,
subspace.
Subspace.
Now I'll tell you in one order. You repeat that.
Okay, sir.
Vector space, subspace, basis, dimension.
Vector space, subspace, basis, dimension.
This is only for which students?
See.
If you are preparing for any interviews, master interview, research interview, PhD interview, for sure you will get questions from this topics. Okay. So let's ask Hussein few things. Hussein, vector space deals with 4 things here. I'll tell you those 4 things. You have to repeat. Okay.
Okay, sir.
Vector space deals with 4 things. They are 2 set of vectors and 2 operations. It deals with what?
2 set of vectors and 2 operations.
Operations. Let the first set be represented with V. Okay, I said 2 sets, na? 2 sets of vectors. The second set be represented with F. Is that okay?
Okay, sir.
And the operations are very simple. One is vector addition, the other is scalar multiplication. Is that clear, Hussein?
Yes, sir.
I'm going to play with 4 things here. One is a set called V, set called F, vector addition, scalar multiplication. Is that okay?
Okay, sir.
Can you tell me what are the things I said?
There are two sets V and F. The two algebraic operations are performed: vector addition and scalar multiplication.
Okay. Are you aware of vector addition?
Vector addition.
Can you add two vectors?
Yes, sir.
We add vectors component wise.
Yes.
Correct?
Yes.
Scalar multiplication means, suppose if x is a vector, do you know how to find kx?
Yes, sir.
Very simple, na?
Just multiply.
Multiply. Whatever I said looks simple or not?
Yes.
But when it comes to the problems, it is not that simple. Okay. Once again, I'll tell you, vector space deals with four things. Among the four, the two are the two sets, which I call as V and F. The other two are very simple: vector addition and scalar multiplication. Okay. Hussein, are you ready?
Yes, sir.
What is V? Read it.
V is a non-empty set of objects called vectors.
It's a set of vectors, it seems. Okay. Instead of set of vectors, you can also have matrices. What does V contain?
Vectors or matrices.
Yeah, it contains set of matrices or set of vectors. But in today's discussion, I'll limit myself to vectors only. So you have only these vectors in your syllabus. What is F?
F is a scalar field for USF is either the field of real numbers or the field C of complex numbers.
F means for us, it is set of real numbers or set of complex numbers. Okay.
Okay. Sir.
Once again, what is VR? Tell me.
V is a non-empty set of objects called vectors or matrices.
It is simply set of vectors. Okay. What is F?
A scalar field for us, F is either the field of real numbers or the field C of complex numbers.
So it is simply a set of real numbers. Do you know real numbers, na?
Yes, sir.
Okay. Vector addition also you know.
Yes.
Scalar multiplication also you know.
Yes, sir.
Right. Vector addition means if x is a vector, y is a vector, x plus y is vector addition.
Yes, sir.
Scalar multiplication means if alpha is a scalar, x is a vector, then alpha x is nothing but scalar multiplication.
Yes, sir.
Now see here, from where this alpha is coming?
Alpha on constant.
From
set of real numbers. Set.
From where x is coming?
From V.
Yes. Now if you look at this x and this y, from where x and y are coming?
V.
Now it is simply vector addition. That means you already know how to add the two vectors. Is that clear?
Yes.
Can you tell me in short what we have discussed so far?
We discussed about vector space. Vector space has two sets, V and F. V is an odd-empty set of objects called, it contains vectors. So F is either a field of real numbers or a field of complex numbers.
In short, it is set of real numbers or set of complex
numbers. So yes. So we are dealing with two operations: vector addition and scalar multiplication.
Okay.
Vector addition is done by x plus y. We select elements from the set V. And scalar multiplication is denoted by alpha x. We select alpha from F and x from V.
Okay. So far, this looks as if these are the contents for a 5th or 6th class, correct?
Yes.
Yes or no? Okay, fine. Okay, I also agree to that. Let me read it. Okay, in many of the interviews they ask this. Look at it. What is the definition of vector space now? The set V is called a vector space over F when vector addition and scalar multiplication satisfy the following properties. Is that clear?
Yes, sir.
The set V is called what? Vector space whenever it satisfies the following properties. Can you read the first one?
x plus y element of V for all x, y element of V. This is called the closure property for vector addition.
You know what is this saying? You take any two vectors of V. If you add, the resultant should also be in the set V, it seems.
Yes, sir.
Okay, listen to me carefully. You take any two vectors from the set V. If you add, the resultant should also be in the set V. Read the second one, dummy property.
X plus y, the whole plus z equal to x plus y plus z.
Yeah, this should be true. Okay.
For all, third x plus y equal to y plus x for every x, y element of V.
The last two are very, very important. Read the last two.
There is an element 0 element of V such that x plus 0 equal to x for every x element of V.
What is this guy saying is, if you have to call a set V as vector space, for sure 0 vector should be a part of it. Okay, he's constructing few rules here. He's saying if you want to call V as a vector space, for sure 0 vector should be a part of it. Is that okay?
Yes, sir.
This property, that is x plus 0 equal to x, is called additive identity. Okay, next to read the last one.
For every x element of V, there's an element minus x element of V such that x plus minus x equal to 0.
If you have a vector called x from V, then minus x should also be a part of that set, it seems. Is that clear?
Yes, sir.
Now I'll just highlight the important ones which you have to check. These are the important ones that you have to check. This you need not check. This would be true. Can you tell me what the first property is saying?
Closure property.
Yeah, can you just briefly explain us?
X plus y is an element of V for if and x and y are element of V.
You should have explained me like this. Take two vectors from V. If you add them, that resultant should also be part of what? V.
Okay.
Okay, is that clear?
Okay.
0 vector should also be part of your set. Is that okay?
Yes.
If x is a vector in V, minus x also should be a part of that. Yes or no?
Okay, sir.
These are the rules. These are under vector addition. Okay, let's see rules under scalar multiplication. So I'll talk to some other student for that. Okay, when we solve the problems, people will definitely enjoy those problems. Yes.
Yes, sir.
What we have discussed is under vector addition. Now scalar multiplication. Can you read these properties?
Alpha x belongs to V for all alpha belongs to F and x belongs to V. This is called closure property for scalar multiplication.
What he's saying is you take a vector called x and take a scalar from set called F. Alpha x should also be part of what? V.
The V set.
Right. Next property you read.
Alpha beta multiplied by x equals to alpha multiplied by beta x for all alpha beta belongs to set F and every x belongs to V.
Right. These two properties are very, very simple. Okay, I'll not focus on this. Yeah, go through the third one also.
Alpha plus beta multiplied by x equals to alpha x plus beta x for all alpha beta belongs to F and every x belongs to V.
The last one.
1 into x equals to x for every x belongs to V.
Okay, these three are very, very trivial ones. No need to be checked. Only this must be checked. Okay, what is this saying? Not this one. I'm sorry. The first one. If
Yes,
x
sir.
is a vector, alpha x should also be part of what?
The set V.
Where from where alpha comes?
Sir, from the set V only.
Alpha comes from.
Sorry, from set F, the set of real numbers.
From where x comes?
Sir, from the vector space.
From the
set
set
V.
V.
Yes, sir.
Alpha x should also be part of what?
The set V, which is the vector space.
Okay. Now, can you just give me a recap? Vector space deals with 4 things. What are they?
Sir, set V, which is a set of vectors, and a set F, which is a set of real numbers or complex numbers, and two operations, which are scalar multiplication and vector addition.
Now we have some rules under vector addition. We have rules under scalar multiplication. Any set V satisfying these properties is said to be what?
Any set V satisfying these properties is said to be able to perform vector addition.
No. Is said to be vector space.
Sir, can you explain this thing?
Any set V satisfying all these discussed properties would be called vector space.
Okay, sir, got it.
That set V would be called vector space. Okay.
Space.
One more small definition here. Read this.
Subspace. Let S be a non-empty subset of vector space V over F. If S is also a vector space over F using the same addition and scalar multiplication operations, then S is said to be a subspace of V.
What we are doing is, earlier we gave rules for vector space. Am I right?
Yes, sir.
There is a set called V. If it satisfies properties under vector addition, if it satisfies properties under scalar multiplication, such a set V would be called vector space, correct?
Yes, sir.
Now what we are doing is, we are taking subset of V.
Yes, sir.
Subset means what?
Some elements.
Some elements of V. If that also satisfies vector addition properties, scalar multiplication properties, then such a set would be called what?
Subspace of V.
Subspace. Is that clear?
Yes, sir.
Now guys, the properties that I discussed look so simple, but look at the problems. Look at the problems. First problem, this fellow will solve for us. Okay. Who? Yash will solve. Yeah, read it, Yash.
Determine which of the following subsets of R raised to the power n are in fact subspaces of R n. X belongs.
Wait. I'll help you.
Yes.
You. He's asking which of the sets are subspaces. What does this R power n mean?
Sir, real numbers?
No. It is containing a vector in R power n dimension. That means it will have n components.
Okay.
I'll give you one example. Don't get confused. Suppose, example. If I say R power 3, then every vector is like this. If you say R power 4, then the vectors are like this. If you say R power n, then every vector that you take would be like this. Is that clear?
Yes.
Okay. So he's talking about R power n. Let's make this discussion very simple. I'll solve the first one. I'll set n as 3. That means I'm just looking at vectors in the 3 dimension.
Yes, sir.
Okay. I'll also help you to read this. X is a set of vectors such that x1, okay, I have removed that dot. X1 is greater than or equal to 0. Okay. I'll help you, my dear students, I'll help you to read this again and again. You just have to create vectors in R power 3 such that the first component is always greater than or equal to 0. Can you give me such vector, Yash?
Yes, sir. Sir, it 0, 1, 1.
0, 1, 1. Can you give me another vector called y?
Yes, sir. 1, 2, 3.
Okay, 1, 2, 3. Can you give me another vector called z?
Yes, sir. 2, 3, 1.
Yes.
Yes, sir.
Is x, y, z are all part of this? Or let's write simply v1, v2, v3. Let's not get confused. Let me write v1, v2, v3. Is v1, v2, v3 part of x?
Yes, sir.
Because all these first components are
satisfying the property.
Correct.
Greater than this.
Can you tell me what is minus v2?
Sir, -1, -2, and -3.
Can this be part of x?
No, sir.
That means minus v2 does not belong to x. Am I right?
Yes, sir.
If v2 belongs to x, then according to the vector space properties, minus v2 should also belong to x, na?
Yes, sir, but it does not, so it's not a subspace.
Not a subspace. Not a subspace. I'll go to the next student. I'll go to Hussein again. Hussein, are you there?
Yes, sir. Yes, sir.
Hussein, will you help me with the next problem?
Yes, sir.
I'll copy this problem. You need to create such that you need to create vectors in r power 3. So I've taken example as n equal to 3. That means r power 3. Give me vectors such that the first component is 0.
0, 2, 2.
Okay.
0, 1, 2. 0, 3, 3.
Now you add v1 and v2.
0, 3, 4.
Is this part of x?
No.
Yes, it's a part of x because the first component is 0.
Yes, yes, yes.
Yes or no?
Yes, yes, yes. So,
Tell me minus v1.
yes, 1, 0, minus 3, minus 4.
Is it also belonging to x?
Yes.
Okay. Can you tell me what is minus 2 v1?
Minus 2, 0, 0, minus 4, minus 4.
Is this also part of this vector, the set x?
Yes.
Because if you want to call a vector a part of x, the first component must be 0. That's it. Right?
Yes,
It
yes,
looks
sir.
like it is going to satisfy all the properties of vector space. Correct?
Yes, yes.
Therefore, the set of vectors which satisfy where the first component is
1
0
equal to
is
0.
going to form what?
So, vector space.
Subspace.
Subspace.
He's asked us to check whether it's subspace or not.
Subspace.
Okay, I'll go to another student, Karuna.
Sir,
Not Karuna,
just a second. Sir, can I just, sir, in the first part also x1 greater than equal to 0, that x1 was referring to the first element of the vector only.
Yes.
Okay, sir.
But here I am also referring to the first element, but that first element is not greater than or equal to 0.
Yeah, sir.
Okay. Is that clear?
Yes,
Karunya.
sir.
Yes, sir.
Oh, I'm so Karunya. I'll go to the third problem. Karunya.
Yes, sir.
I'll again set n equal to 3. Give me vectors from r power 3.
Yes, sir.
Can you create some vectors?
0, 1, 2.
0, 1, 2. Okay.
V2. 0, 1, 3.
Create some new vectors, yeah.
Okay. 0, 4, 5.
No, I'm going to create like this. 2. Give me the next entry.
3, 4.
No. You need to create it such a way that when you take the product of first two, it should give you 0.
Okay, sir. 0, 0.
Next, it can be anything. V3, please.
You want to make it V1, V2 as zeros.
I want to make this into this to be 0. This into this to be 0.
Sir. Okay, sir. I got it. Okay, sir. 11, 0, 1.
11, 0, 1. Okay. Fine. Add V1 plus V2.
2, 1, 7.
2, 1, 7. What is the sum?
3. V1 plus.
So this plus this is 3, na? Clearly
Yes,
this doesn't belong to X.
Yes, sir.
Okay. So it's not a subspace. Not a subspace. Right. So what I have given is some introduction to vector space.
Yes.
Vector space deals with 4 things. One is set V, set F.
Set F, vector addition, scalar multiplication.
There are certain rules under vector addition, scalar multiplication. If a given set satisfies all of them, then you can declare such set to be vector space. Is that clear?
Yes.
There are 2 more things that are left over. One is basis, the other is dimension. I'll discuss that and then end this session. Okay, just give me a second. Yeah, are you there, Karunya? Hello.
Yes, sir.
Yeah, so let me tell you what is this basis, what is dimension. See here, a linearly independent spanning set for a vector space V is called basis. Okay, I'll help you. Suppose imagine V1 is something like this. V2 is like this. V3 is like this. With the help of V1, V2, V3, can I represent any point in R3?
R3, sir. Yeah, V3.
Give me some point or some vector in R3.
It's the same vector combination or different?
No, you just randomly give me a vector in R3. Randomly.
10, 5, 7.
I have taken minus also to just, okay. Can I represent this vector using V1, V2, V3?
10 times of V1, 2 times, 5 times of V2 and minus of V3.
Now what I want to say is, suppose you want to represent any vector space. You know what does vector space mean? Okay, it contains some set of vectors. To span, that means to represent any vector in that set, you need some linearly independent vectors. For example, V1, V2, V3, will they form linearly independent vectors?
Yes, sir.
Like that, every vector space needs some set of linearly independent set. Okay, such set is called what? Basis.
Basis.
Okay, basis. For example, can I say here V1, V2, V3 span R3? Can I say that?
Yes, sir.
When I say span R3, that means I can represent any point using V1, V2, V3, correct?
Yes, sir.
Look at another set here. Let's name it as X1, which is 1, 0, 0. X2 is 0, 1, 0. I gave only 2 vectors, X1 and X2. Can you represent or can you span R3?
Yes, sir. It's 0 times of X.
Can
So
you
before
span
10, 5
R3?
minus.
Using X1 and X2, we cannot span R3. Am I right?
And we write 0 times of X3.
Where is X3? I have not given you X3, na? I gave only 2 vectors.
I said 0 times of anything. Actually not mentioned.
See here, I'm trying to give you a vector called Y, something like 1, 1, 1. Can you represent Y using only X1 and X2?
No, sir.
It's not possible. That means what? X1, X2 will not span
R3.
R3. Okay, so first of all, I need all the vectors which are going to span the vector space. Those vectors should be linearly independent. Such set is called what?
Basis.
Basis. Now look at the definition of dimension. What is dimension?
Dimension of a vector space V is defined as dimension V, number of vectors in any basis for V.
Once you construct the basis, you have to count the number of vectors in that.
Yes.
Is that clear?
Yes, sir. 3 vectors.
Once you construct the basis, you simply have to count the number of vectors in that. Okay. So mostly, I mean, if you look at the gate, there are very, very few questions that were asked in the gate exam. So if you have got this knowledge, that is all these rules, whatever I said, you can actually handle the questions on vector space. So this is where I'm going to stop, and I'm going to take the doubts from you people.
Homework problem is not explained.
Just a minute. You have a doubt?
Yes, sir.
Yeah,
Homework problem. The maximum determinant value possible for a given matrix of trace 14.
Okay. What is your doubt in that?
So you gave it as a homework, we solved it. So what is the answer?
49 is the answer.
Yes, 49. Okay, sir. I got it.
Okay. I'll take other doubts also from the students. Let me talk to other students. Mahati, what is your doubt?
No doubt.
No doubt. Okay. Let me lower all the hands once again. Whoever has the doubts can raise the hand. Okay. Let me first lower all the hands. Yeah, Deshpande.
The problem which is said you will discuss about the non-basis columns.
The problem which I?
You told you will discuss non-basis column on second problem of first class. Sir.
Okay. Oh, you are the one who are asking that. See here.
Yes, sir.
Even, okay, I'll directly discuss that problem with you. I'll copy these equations.
Yes, sir.
You have to help me quickly, okay?
Yes.
This is the general solution, am I right?
Yes, sir.
Let's put K1 equal to K2 equal to 1.
Yes, sir.
Can you generate
minus 3 1 0 1 1
minus 3
1 0 1 1 1
minus 3 1
0 1 1
1 1. Okay.
Yes, sir.
Give me the first column.
First column is 1 2 1 3 3 5
1
3
2
3
1 2
1 2 1 3 3.
No, 1 2 1 2. First column of A I'm asking.
Okay. First column of A 1 2 1 2. Yes, sir.
It should be multiplied with what?
Minus 3 plus 1 into second column 2 4 2 4.
Next.
And the next is 0 into 1 0 3 0.
Anything would be 0 only.
Yes,
okay.
sir. 1 into 3 4 5 4. And 1 into 3 4 5 7.
This should give us 5 6 9 9. Na?
9 9. Yes, sir.
Okay. Give me the first element.
Minus 3 plus 2 3 6 6 3 5.
Second element.
Minus 6 4 is 2 minus 2 8 is 6.
Next element.
Yes, sir. Got, sir.
Complete it.
5 6 9 9, sir.
So it is verified, na?
Yes, sir. But
maybe some simplification you have done wrong.
Okay, sir. Okay, sir. Sir, and another thing, sir, for general solution, how we did know, sir, here, we got two independent sums, two independent columns, no, sir.
Which question are you talking about?
Same question, sir. We got K1 into general equation, sir. In this, there are two independent columns, sir.
We usually don't talk about linearly independent solutions for a non-homogeneous system.
Okay, sir. Then how to find in basis and all, sir? How to find that it is spamming itself?
Basis dimension are not applicable to this.
Sir, then they will give a vector and they ask that which are the basis, which are the vectors spamming the vector, sir?
Mostly you get a question like, I'll tell you what kind of questions you'll get. They'll give you some set of vectors. They'll ask whether this is a vector space or not, like what we have discussed in the class.
Yes, sir.
What else they can ask is, they'll give you a system called A.
Yes, sir.
X equal to 0.
Yes, sir.
Okay, they'll give you a system called Ax equal to 0. There is a set called X, na?
Yes, sir.
What is X? X is nothing but the solutions.
Yes, sir.
So for example, let the set contain infinitely many solutions.
Yes, sir.
So X is nothing but set of all those solutions which satisfy Ax equal to 0. Is that okay?
0. Yes, sir. Yes, sir.
They'll ask what is the basis of that.
Okay, sir.
The basis of that is simply n minus r.
Yes, sir.
Because n minus r indicates what?
Number of infinite. How many
number of linearly independent
solutions?
If you have that knowledge, that is enough.
Okay, sir.
Yeah.
Thank you,
Any
sir.
other
Thank
doubt?
you, sir. No, sir. Thank you.
See, what I'll do is I'll upload the complete notes also. Today's notes I'll upload as well as the complete notes. Tanmay?
Sir, for civil engineering, vector spaces is doesn't needed to prepare, sir.
Not there, I clearly said, na.
Okay, sir. Sorry, sir. Thank you.
Azad? Azad Pallam?
Sir, can you listen? Can you hear?
Yes, you can ask.
Sir, on the example before you said before the basis, sir.
Okay. So what is your doubt?
Sir, should we need to check each and every property of vector addition and scalar multiplication?
No. Only like properties like you take any two vectors. If you add, the resultant should also be a part of that. Okay.
What if
should also be a part of that?
What if two subsets satisfy the vectors?
See,
vector
they'll
space.
give you only one set of vectors. Okay.
Sir. Okay, sir.
They'll ask you, is a given set a vector space or not?
Yeah, okay, sir. So, and the other doubt, eigenvectors with distinct eigenvalues are linearly independent. Is this always true?
Always true.
Yeah, okay, sir. So could you please go with any example?
Go with?
Any example?
We have discussed some examples here. I'll put
Yes, sir.
that in front of you.
Yeah, that's it.
But those examples were very simple. 2x2 matrix.
Yes, sir.
Look at this matrix. What are the eigenvalues?
Minus 3. Okay. Alpha 1 and 5.
1 and 5, correct?
Yes, sir.
We got two eigenvectors.
Yes, sir.
Those two eigenvectors are E1 and E2. Let's
E1
say.
and E2. Yes.
We checked that they are linearly
independent. Yes, sir.
Because for 3x3, the calculations becomes very, lengthy, na?
Yeah. Yes, sir.
In the exam, they will
So-
not ask you to find the 3. They'll ask how many
Yeah.
are there.
Yeah.
That's
So
why
so
I've
it
not
so it
calculated.
always works.
Always true.
Yes, sir. And could you please explain that diagonalizable one, sir, briefly?
No, what is your doubt? You tell me. I
Sir,
can. You want me to explain it again or what?
just brief it, sir. I couldn't get.
If you can tell me where, like, you felt difficulty, it would be good. See,
Sir,
once go through this.
Yes, sir.
Hmm.
A equals to on that solvation. A equals to PD.
This one.
Yes, sir. Yes.
Let's say A is diagonalizable. That means you are able
sir.
to write A as P D P inverse.
Yes, sir.
What would be A square? A
A into A. Yes, sir.
What is A?
PD P inverse.
What is another A? PD
Yeah,
P
PD
inverse
P
only,
inverse.
na?
Yes, sir.
What is P into P?
Yeah. Okay, sir. P inverse. Yeah, I, sir.
Sorry, not P into P. P inverse into P.
P inverse into P. That's maybe I, sir.
I. D into I.
Into I D.
D into D.
D into D square. Sorry.
That's what is written here.
Yeah. Okay, sir. Sir, does this like when we go through this process while finding a power n, so won't it take more time, sir?
That's what now. If you go by the usual way of finding A power 100, it will take more time. But if you go with diagonalizability, it will take less time.
Okay, sir.
Here only 3 multiplications are involved. One is
Yes, sir.
not 3, 2. P with
Yes, sir.
D power 100.
P with D power
and the resultant with P inverse.
Yes, sir.
And how do you get D power 100 is very simple.
Yes, sir. Thank you, sir.
Yes. And my dear students, if you have doubts, we are there in the Telegram channel, in the groups. Don't message me personally. You put your doubt in the groups. The other students will also help you, or like they may also have the same doubt. So always use groups. Ace technical, Ace non-technical groups. You try to post your doubts. Dhana Sriram.
Hello, sir.
Yes.
Sir, page number 89.
The page numbers might got changed. Okay, is this your question?
Sir, this question only, sir.
Hmm.
So it can be also AB equal to BA, sir.
There are some instances where AB can be BA, but it's not always true.
Okay.
I want a statement which is always true, but that is not always true.
So why can't we go with the general solution, sir? Instead of going with 1, 0, 0, 0, we can go through
Actually, I
A.
can find not only this matrix, not only this set of matrices, I can create few more sets actually which do not satisfy this property.
Okay, sir.
So understand that usually when you are dealing with matrices, AB need not be equal to BA. It is not 2 into 3 equal to 3 into 2. It's not like that. Na? This is some matrices. Row time column multiplication is involved. So AB may not be equal to BA. That's a trick here.
Okay, sir. Yes, sir.
Okay.
Yes, sir.
Yeah. Let's talk to Pavitra Sai Kalyan. Pavitra, your audio was not clear. I'm sorry. I mean, now let's check. Yeah. What is your doubt?
Sir, yesterday's homework problem, can you explain it, sir?
Which one?
So the maximum value of determinant among all 2 cross 2 real symmetric matrices with trace 14.
Okay. So what is determinant A here? It is AC minus B square, correct?
Yes, sir.
we want to maximize this determinant, you will get the maximum value only when b is 0.
Okay, sir.
Why? Because if b is not 0, every time you are subtracting something from AC. Is that clear?
Okay, sir.
If someone is
Yes, sir.
subtracting your money, how can you maximize your income, yeah? So first
Yes,
make
sir.
sure this b is 0.
B is 0.
So I'll write now what is det A value?
AC.
AC. Is there any other connection or condition given in terms of A and C?
A plus C is equal to 14. Trace of A is equal to 14.
So now we have a condition like maximize AC such that A plus C is 14. Am I right?
Yes, sir.
Now what is C from this?
A minus 40. 14 minus A.
So you just have to maximize what? A into 14 minus A.
Yes, sir.
Which is like
14A minus A square.
This looks like a function in A.
Yes, sir.
So treat this as f of A. So to get the maximum value, we need to find f dash of A, which is 14 minus 2A. Equate that to 0. With that, you get A equal to what? 7.
7.
You also check for the second derivative sign, which is minus 2. The derivative of 14 is 0. Derivative of minus 2A is minus 2. Correct?
Yes, sir.
This is less than 0. If this is less than 0, that means f of A maximizes at A equal to 7. Okay?
Okay,
So what is
sir.
the maximum value now? Is 14 into 7 minus 7 square. That is 49. Okay? 14 sevens are 98. 7 square is
So
49.
how do we f of A is maximizes at A is equal to 7?
Because see here, calculus course is not over, na? So usually when you have a function in X or function in A, we go for the first derivative, equate that to 0, get some points. We call
Okay,
those
sir.
points as stationary points. At those stationary points, check for the second derivative sign.
Okay,
If the
sir.
second derivative is less than 0, then the function maximizes at that point.
Okay, sir.
All these things would be taught to you in a course called calculus.
Yes, sir. So the next doubt is in today's topic.
Yes. Yeah, tell me what is your doubt.
Page number definition.
Page number?
$166, sir.
Yes.
So 166.
This one?
So here, yes, sir. So here A cube is equal to F A square minus 4A. The next step, how does the next step arise?
Instead of A square, instead of this A square, what is A square value earlier?
5A minus 4.
Substitute that here, huh?
Okay, okay, sir.
Hmm.
Okay, sir. Thank you, sir.
Okay. Sai Kalyan?
Hello.
Yes.
Sir, I am having a doubt regarding yesterday's class, sir,
Hmm.
regarding the topic of unitary matrix.
Unitary matrix. What is your doubt?
Hello, sir. I said unitary matrix is similar to the orthogonal matrix, right?
Hmm.
So in the unitary matrix, the length of the column is also will be equal to unity.
Hmm.
If this holds true.
In unitary also it's one only.
Can because the example which you gave yesterday for the conjugate of a matrix, can you can you tell me that explanation regarding that? For example, this example unitary matrix 1 plus I by 2.
Find the length, na?
It's getting root I here. That's why I'm not getting 1.
You have to take modulus of that.
Square root of 1 plus I whole.
Okay. First. Yeah, I understood your doubt. See, for complex vectors, it would be a little different. Okay, complex vectors, it would be a little different.
Okay, then it can't be the length of the column can't be unity.
It can be unitary, but I mean it can be unit, but the definition is slightly altered. I mean, usually in orthogonal matrix, what we do is we simply square each and every element, na?
Yes, sir.
Here you first take the magnitude, individual magnitudes, and then square add it.
Okay.
Okay.
Okay, sir. Okay, sir.
And then verify it. You will get it.
Okay, sir. And one more thing here, I just need regarding clarity of the diagonalization. How can you say a matrix is a diagonalization?
See, that is a difficult task actually. I'll just
No,
tell you
I'll
the
just
condition
regarding
for
the-
diagonalizability.
Okay.
The condition is if a matrix has n linearly independent eigenvectors.
Okay.
If a matrix has n linearly independent eigenvectors, then it is diagonalizable. That is not in your syllabus also actually. Diagonalization is not in your syllabus. Only like to explain you the application of geometric multiplicity, I have taken that.
No, sir. For example, if you're saying you have two different eigenvalues, then we are having n different eigenvectors, right?
If you let's take a 2 cross 2 matrix, it has got distinct eigenvalues, then that matrix is diagonalizable.
Okay. For example, even if you are having two eigenvalues same and other value is different, even also you are getting n eigen.
That's
right?
what. Because of that, what I'm saying is, I'm not saying that distinct eigenvalues means diagonalizability. I'm just saying it is diagonalizable whenever a matrix has n linearly independent eigenvectors.
Okay.
Okay.
Okay,
When
sir.
do you have? When can you have n linearly independent eigenvectors? Case one is when the matrix has got n distinct eigenvalues. That is one case. There is one more case where you can have n linearly independent eigenvectors. That is, if some of the eigenvalues are repeated, then also a matrix can have.
Yes, sir. Yes, sir. Okay. Okay. Is this n is like is that order of the matrix?
Order, yes.
Okay. Okay, sir. Okay. Okay. Thank you, sir.
Yeah, Sachin.
Sir, I just wanted to know that where these materials are being uploaded, sir, because in the student portal I could find EDC material which isn't related to this.
Oh, you are, see, for that you have to talk to the manager or your friends. I can't help you regarding that.
No, sir, actually I didn't find this max materials. That's why I was asking.
What max material you want? Max material?
You said the previous, yes, sir, whatever you explained just now. So the previous class, all these things will be uploaded. You said no, sir.
Yeah. See here, the way you watch the video. Did you watch the video?
Yes, sir.
Recorded video.
Yes, sir. Yes, sir.
There would be a something called as content.
Okay.
In content, you will see recorded video, and below that you will see running notes.
Okay. Okay.
In that running notes, you will see this notes.
Okay, sir. Okay.
Okay, so please go through that and let me know if you have any difficulty. I can mail you. I can send you the notes also.
Okay, sure, sir.
So see here, I can mail you today's notes, but tomorrow another faculty will come. He may not send you the notes.
Yeah, yes, sir.
The best way is to download the notes on your own.
Okay, sure, sir. I'll do that.
Okay, because all faculty will not have the notes. Some faculty will only will be having. Other faculty will just send the file to the manager. The manager will upload the notes.
Okay, sir.
So make sure you download the notes on your own. There's a section called contents. In that, recorded videos and running notes are there.
Okay. Okay, sir. Thank you, sir.
Yeah, Chandrika.
Hello, sir.
Yes.
So could you please explain basis once again? I missed it. I mean, I could not.
Okay. See, basis means it contains, first of all, shall I explain you using an example?
Yes, sir. That would be great.
Yeah. So I'll just give you, are you from EC?
Yes, sir.
Suppose there's a system called AX equal to 0. Let's say this system has infinitely many solutions.
Okay.
Okay. This system has got how many solutions?
Okay.
Infinitely many solutions.
Infinitely many.
You write general solution, na?
Yeah.
How do you write general solution? X is something like xf1 h1 plus xf2 h2 plus so on xf n minus r h n minus r. Am I right?
Right.
Now, can I say that using h1, h2, h n minus r, can I generate all possible solutions? Yes, I can generate all possible solutions with h1, h2, so on, hn minus r, correct?
Yeah, right.
Simply take the linear combinations.
Okay.
In other words, you give me any solution, I can represent that particular solution as linear combination of all this n minus r vectors.
Right.
Correct?
Yeah.
That means, are you able to span your solution set? Are you able to represent your solution set with this n minus r vectors?
Yes, I am.
In such case, h1, h2, hn minus r are termed as basis.
Okay.
The set h1, h2, so on, hn minus r are termed as basis. And how many vectors are there in that set?
N.
No.
Sorry.
H1, H2,
N
so
minus
hn,
N minus R sets. Yeah.
N minus r is called the dimension of that solution set now.
Okay.
Okay. And such set h1, h2, so on, hn minus r is called your basis.
Okay.
They will definitely ask questions this way. They'll give you a system called AX equal to 0. They'll ask, what is the dimension of your solution set X? The answer is n minus r.
Okay. But I think you also gave us an example that wouldn't form such a combination.
No. That is a different case. That is, I gave you some set of vectors and I'm asking whether it's a subspace or not.
Okay.
I gave you one set. So I'm asking whether that is going to form a subspace or not.
Okay,
so verify the rules of the vector spaces.
Right. So whenever I'm given a set of vectors and I'm asked to check if the given vectors form bases, I'll just check if they have infinitely many solutions. That would be sufficient, right, sir?
See here, you are from EC. What I'm saying is, for sure, you might get a question called, consider a system called AX equal to 0. Okay. Consider a system called AX equal to 0. They'll ask, what is the dimension of X?
Right.
What you are supposed to do, find rank of
Rank.
A.
Yeah.
You know number of variables.
Yeah.
The answer is n minus r.
Yeah, right.
Okay, so this is enough for you for EC
Okay.
students. If you
Okay.
think beyond that, there is something called range space, okay, which is called column space, row space, null space. These are all like too much for you.
Yeah, yeah. Okay, sir. Okay.
Yeah.
Thank you so much, sir.
Yes. Krishna Vamsi.
Sir, could you please resend those Telegram links once more? I think I lost it.
Okay, I will do that.
Thank you, sir.
I need some time. Just give me a moment. I'll copying that. Okay, I'll do that in some time. Udayshri, what is your doubt?
Sir,
Yeah, who is talking to me?
sir, Krishna Vamsi.
Krishna Vamsi, you asked for Telegram channels, na?
Sir, another is that actually yesterday in yesterday's class you said one property of rank will be discussed later. Rank of a
I
denotes
have
size
discussed
of
that, na? Number of.
rank of a denotes size of the largest non-zero minor of matrix A.
Your voice is not audible. Please repeat your doubt.
Sir, rank of a, yesterday in last class, you will say that you said that rank of a, this property rank of a denotes size of the largest non-zero minor of matrix A. That will be discussed later. Have you in what way have is this discussed, sir? Will be
Yes, it is discussed in detailed way. Check it.
So rank A denotes the number of linearly independent rows. It's not discussed.
That is also discussed. Linearly independent vectors. What did I tell there? Hello?
Yes.
Yes, sir.
While discussing linearly independent vectors, the rank denotes the number of linearly independent vectors. Yes or no? Hello?
Yes, sir. Yes, sir.
So under the topic of linearly independent vectors, I have discussed that. So usually what rank denotes, suppose you want to find rank of a matrix called A. Let's say you got rank to be 2. Suppose it's a 3 cross 3 matrix and the rank is 2. That means it is indicating that there are only 2 linearly independent columns or only 2 linearly independent rows. That's what it means.
Okay.
Okay. So under the concept of linearly independent vectors, I have covered that. Please go through it once. If you have doubt, I'm there to help you now. Yukta, what is your doubt?
Sir, you said the statement like when lambda is, when eigenvalues are completely distinct, there will be n independent eigenvectors. Sir. Out of infinity eigenvectors, there will be only n independent eigenvectors. Sir.
Yes. Just like infinitely many solutions, there are n minus r linearly independent solutions, not like that. Hello?
So, and basis also, sir, like if you can denote all the vectors in vector space by some set of vectors, that is called basis. Is that right?
See here, first of all, basis means it should cover your whatever like set. For example, here ax equal to 0 means there is some set called x which satisfies ax equal to 0. Okay. Hello?
Yes, sir. Okay, sir.
Consider a system called AX equal to 0. Let's say that system has got infinitely many solutions. Is that okay?
Okay, sir.
So now what X contains? It contains all those solutions which satisfy AX equal to 0.
Yes, sir.
Are you following?
Yes, sir.
I'm saying consider a system called AX equal to 0, which has got infinitely many solutions.
Yes, sir.
After writing its general solution, it looks like xf1 h1 plus xf2 h2, so on xf n minus r hn minus r, correct?
Yes, sir.
All those solutions can be formed using linear combination of this n minus r vectors.
Yes, sir.
Okay, all the solutions I can represent using this n minus r vectors. So this n minus r vectors, which are called in this case as h1, h2, hn minus r, form basis.
Yes.
Okay, you put all these vectors in one set. That set is called basis.
Yes, sir. Okay, sir.
So what that set contains? It contains h1, h2, so on hn minus r. If you count the number of vectors in that set, it is clearly n minus r. Okay?
Yes.
That n minus r is called dimension of that set. Hello?
Yes, sir. Clear, sir.
Yeah, is that clear?
Yes, sir.
Pavan.
Hello, sir.
Yeah.
My doubt is regarding yesterday's homework question, sir. Trace is equal to 14.
Yes, I have explained that problem
Yes,
just
sir.
now.
Sir, I have a solution, sir. A plus C equal to 14, sir. Can we put A and C some values, sir, that we can get the maximum value?
That is not authentic actually. How many values? You can put A equal to C equal to 7, A
Yes,
as
sir.
8, C as 6, A as
5,
6.5, A as 6.5, and C as
Okay, okay, sir.
7.5. There are infinitely many possibilities there.
Okay, sir.
You will not know which is going to give you a maximum value.
Okay, sir.
Yeah.
I thought it's some approach.
That may backfire also.
Okay, okay, sir. Sir, another doubt is what is meant by nullity, sir? I didn't understand that term yesterday. Nullity of a matrix.
Is very, very simple. Okay. Suppose n cross n matrix is given to you.
Okay, sir.
Can you find the rank?
Yes, sir.
Then nullity of that matrix is simply n minus r.
Okay, sir.
Yeah, that is that much simple.
Okay, okay, sir. Thank you, sir.
Usually the term nullity is not used in the GATE exam. In our workbook, for certain problems, they are using that term. Usually in the GATE terminology, no one is using the term called nullity. Okay, you can
Okay,
check your previous GATE questions also.
Okay, sir.
Yeah, any other doubts you have, please let me know. Guys, I just want to tell you one thing. Just by watching the videos, okay, you will not be able to get a merit rank. What you have to do is, whatever we have discussed, you have to take that to the next level. It means learn new things day by day. How do you learn new things is by solving good number of problems which are there in our textbook, which are in our previous GATE questions. You can also get the knowledge by writing mock exams. Very, very crucial. So textbook solutions you have to do, previous GATE you have to solve, mock exams you have to write. If you do these three things properly, your preparation would be to the next level. Yeah, Akshaya, I'm sorry, yaar. What is your doubt? You are unable to speak, na? Okay, let me know in the chat. This chat is not visible, yeah. That's the problem. Otherwise, I would have read your doubt. I'm unable to read your chat actually. Akshaya, what you do is you mail me in the Telegram. I'll help you. See, the problem is your messages are not visible to me. You are unable to talk. I can't Take your doubt. Your messages are not visible to me. Yeah. Don't repeat this with other subjects. Make sure you have one nice mic. Arey, you people will play games, na? For playing games, you buy nice accessories. For the class, you are unable to buy. You borrow with your friends. You
Sir,
mail
I
me your
have a
doubt.
doubt. Sir, for rank A denotes number of linearly independent rows or columns. That point, sir.
Yeah, what is your doubt?
Sir, am I audible, sir?
You are audible now.
Sir, for matrix 1 0 1 0 1 1 and 0 0 0, here we have found that vectors are linearly dependent, sir, and the rank of matrix is 2.
Wait. Give me the entries.
1 0 1 0 1 1 0 0 0.
Okay. See here. What is rank?
2.
2. What is this telling? Among the 3 columns that are sitting here, there are only 2 linearly independent XMs.
Yes, sir.
Is that clear?
Yes, sir.
What is your doubt now?
Sir, but for vectors, in finding the vectors are linearly independent or dependent, the vectors are linearly dependent to each other, sir.
See here, rank of a matrix we are talking about. You are going to vectors. Why are you mixing? You want to, can you tell me your doubt clearly? You gave me a matrix. I calculated its rank. I'm telling that there are 3 columns here. Among the 3, there are only 2 linearly independent columns. Is that clear? Hello?
Yes, sir.
Is that clear?
Yes, sir.
What else you want? What else you want to discuss now?
Yes, sir.
What else
I'm
you want?
asking that here the vectors, individual rows, vectors of individual rows are linearly dependent to each other.
See here, you want to talk in terms of rows, then there are 2 rows actually which are linearly independent. Pavitra, see here, Pavitra, I don't get your doubt clearly. Can you come from the beginning onwards once again? What is your doubt? Hello? Hello? Pavitra, you are not there. Okay. Krishna Vamsi, any doubt you have?
Sir, no, sir.
Okay, I'll wait for the student Pavitra. If she is not there, then I'll end the session.
Telegram
Hello,
link.
sir.
Yeah, who is this?
Hello.
Yeah.
Sir, am I audible?
Yeah, you are audible finally. Yeah, what is your doubt?
Sir, can you please go to the 94th page?
94th page, okay. Yes, what is
Sir,
your doubt?
in this question, by making R1 tends to R1 plus R2 plus up to R6 and taking 1 plus alpha out of the determinant.
You're getting alpha as minus 1 or what?
Yes, minus 1.
Okay, once read this.
Oh, sorry.
Read it.
Yes, non-negative value.
He wants alpha which is non-negative. Okay, you are falling into the trap. You are giving one alpha which is negative.
Okay, sir.
Okay. Any other doubt you have?
Okay, thank you. No, sir, that's it.
Okay. Yes, Pavitra.
So sorry for the inconvenience, sir. Here the network is very unstable, sir.
Yeah, it's okay. I can understand that. Your doubt, you are not clear with the doubt. That is my problem. You have, once your doubt is clear, I would be happy.
Sir, no, sir. Here the vectors are in that matrix. The vectors are linearly dependent, sir. So
See, I'll again discuss with you clearly. You gave me a matrix which contains 3 rows and 3 columns, correct?
yes, sir.
If I have to talk in terms of columns, there are 3 columns which are linearly dependent.
Yes, sir.
They are linearly dependent because rank is not 3.
Yes, sir.
Further, what is the rank?
2.
Among those 3, there are 2 linearly independent columns, it seems.
Okay, sir.
Is that clear?
Yes, sir.
Not all the 3 are linearly independent, only 2. That is, any 2 are linearly independent, it seems.
Yes, sir.
Yeah, this is what the rank tells you.
Okay, sir. Sir, another doubt is page number 97. Yesterday's.
Yes. This one or this one?
It is let A be M cross N matrix and B and N cross M, determinant of IM plus AB.
I'll upload that na anyway. See here, I said you have to try. I'll upload the notes I said. This one
Yes,
I think
sir.
you're talking about. Yeah, I'll
Yes, sir.
upload the notes.
So no, so here, how does the property is being used in the sum, sir?
That's what. Don't ever think about that. If you think about that, you'll waste your time. Why you want about this property? He says, na, it's given that.
Yes, sir.
So don't research on that. Try to use that property. That's it.
So without using the property itself, the answer is being arrived.
Using that property also you can do that. I'm going to upload that. I'm saying.
Okay, sir. Okay, sir.
Which is why I said I'll upload is 99.999% students are unable to crack that logic. If you go by that method, you'll waste your time. That's why I'm not teaching you that.
Okay, sir. Okay, sir.
So just to show, I mean, I'll upload the notes. You can go through it.
Okay, sir.
Anyway, I gave you the easiest approach, na?
Yes, sir. Thank you, sir.
Okay, guys. So we
Hello?
had a very long session. Sai Kalyan?
So just have a little more clarity on that. Rank denotes the number of linear independent rows or columns.
See, Kalyan, you have 4 minutes left over. After that, the
Yes,
class
sir.
will be automatically
It would take
over.
only 1 minute, sir. Only 1 minute it will take.
No, I'm just saying, don't misunderstand me. You want to learn about rank?
No. One girl has already spoken to regarding that. Can you just show me that example one?
Okay. Yeah, this one.
Back. Yes, sir. You said 2 are linearly independent, right? Any 2.
Any 2, huh?
So, for example, C1, C2, C1 plus C2 is equal to C3.
Can you speak?
C1 plus C2 is equal to C3, right?
C1 plus C2 is C3, huh?
And for example, if you go for C2 and C3, you can't get C1.
Using C2 and C3, you want to generate C1?
We need to separate or what?
Using C2 and C3 also we can generate C1.
Okay, let's subtraction.
Yes, subtraction. Subtraction is also one form of addition.
Okay. What about C2 and C3, sir? Okay, I understand, sir. I understand.
You take any 2, you can generate the other one.
Okay, sir. Okay, I got it. Okay. Thank you.
Okay, guys. I'm going to end this session. Thanks for attending this. Thanks for being part of ACE Academy.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you,
care.
sir.
Thank you, sir.
Thank you, sir.
Guys, yeah, I'm ending the session. Yeah, it's okay. Bye.